Alright, this is a test. Actually, I think it looks like it's coming through fine. So I recently blocked Google Video on my network because I just wasted too much time on YouTube. I took a week off from work and streaming and stuff just to reset, handle some like life stuff, and I ended up just watching like way too much YouTube, um, which is a hazard going on YouTube. But anyways, um, this week I'm starting on the parallel computing course that I had planned to work on at the start of the month. So let's bring that up. Parallel computing. And this is at Stanford, I think. Yeah, this one here. Close out this stuff here. And I will need to undo this to get access to the lectures because blocking Google Video is going to be an issue here. Maybe I'll just unblock it, download everything. Or I could use YTDLP online to download it. Maybe I'll do that. Just to avoid unblocking it. I want to keep like a healthy distance from YouTube. So I think that'd probably be a good idea. So let's just start with the second lecture. Well, all right, we'll just do all the lectures here. So grab these guys, go to ytdlp.online and paste it in here. Block. Best quality, extract audio, download, subtitles as formats. I think whatever the defaults are is probably fine. Warning, warning, warning. It's a problem with this website is that sometimes it just freaks out. Cannot establish a connection to youtube.com. Interesting. Alright. I think what I'm going to do is switch over to my DNS blocking thing and just re-enable, sorry, not re-enable, disable the block for Google Video. And then I'm going to go to my terminal and I'm just going to download everything using YTDLP from this playlist, which I think I can just say like that. How do I go to the playlist itself? Yeah, this thing here. So let's go over here. We're just going to go to desktop maybe, or maybe go under videos. That's a pretty common location to put stuff. This is going to be CS, we'll say Stanford, CS 149. CD there. And we'll YTDLP this whole playlist here. Alright, well that downloads. So let's go over some of the course material here. So the lectures I have already watched, I believe, all of them. Maybe not all of them. It's been a while. Actually, let me check my other GitHub to see if I have a record of this. 1 second. Nope. Okay, well, we're starting from scratch here. So while that runs, I'll just go over here. I wonder how my audio is. There was someone complaining about the audio yesterday. So I shouldn't say complaining. They're leaving me helpful feedback about the audio yesterday. And they were saying that it's complete garbage. So hopefully this is better. It's hard to tell because I can't monitor my own voice. Maybe I can if I go into options here. Let me try it. Desktop mic. Here we go. Test 1 2 3. Test test test. That seems decent to me. I think I'll give it another listen after this stream is done, just to make sure, but I think that's fine. Alright. So, let's go under, what is this going to be? Source, GitHub, Cypher0. And we need to create a repo for this. We call it just CS149, Kvon, mkdir CS149. I'm going to do a CP of CSAPP readme into here. Obviously, sorry, readme. Obviously, I will not have any of this stuff, so this is going to be parallel computing. And then we got this thing here. Maybe we'll do it like that. And then this will be Kvon. Maybe we do threes here. Bam, bam, bam. Kvon Fatahalian. How did I do this before with that? Okay. And Kunle Alugotun. Okay. See course info for more info on policies and logistics. No. My work on Stanford. I guess I can remove that, yeah. And we'll say CS 149. Parallel computing course. We'll say including, there's no textbook, so here, down here, he has programming assignments. And that won't be a link. I'll just leave that here. Including assignments. And what's in these little sections here? Oh, that's the lecture and video lectures. So I need to create the links for those. All right. Boom, course. will just be the course website here. Lectures will be this playlist here. And then I think I'll do it like that. Yeah, just leave one. The labs, there are no labs for this course. There are no websites. There's no reading, but there are assignments. Okay, so we go over here. So this has, I just want to double check that it matches up with the lectures that are on YouTube's playlist. So we can do a quick length check. So there's 19 lectures in this playlist, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then a final exam. So off by one. Let's go ahead and maybe the additional one is, oh no, that's this one here. Modern multi-core. So this was a two-part, yeah, multi-core part 2 and ISPC programming, parallelizing code. This became parallel programming basics, became parallelizing code. I'm going to go off of these slides because the lectures are a little bit more dated than the slides. So you got parallel computing, parallel programming basics became parallelizing code, and example thought process. Optimization 1 and 2. And then GPU architecture and CUDA programming. And then, actually, I don't think I got past, now that I recall, I don't think I got past locality. Data parallel thinking, efficiency, wait a minute. It's lecture 8, data parallel thinking. Efficiency, evaluate deep neural networks on GPUs. This is where he gets into his hardware lecture. Parallel computing using Spark. I think Spark was just like, okay, we're done with this. Yeah. So that's a bonus lecture there. That might be the extra lecture there. Because that's, I don't see that here. Data parallel thinking. And then we get the DNN and GPUs. Hardware specialization. He talks about cache coherence here, which is different. Programming systems for specialized hardware. He talks about memory consistency. So basically, this Kunle, his lectures are just changing. But it seems like Kayvon has a pretty tight script here. He's been following for a while now. This is 2023 and this is 2025. So, okay, so get past memory consistency, which was programming for system specialized hardware. So mapping AI applications to data center computer. Okay, well, these are totally different. So I'm just going to copy them all, and then we'll do a union of the two. Because the lecture material on the fall 2025 website differs from the lectures on recorded on YouTube 2023, I have union to the slides in the there we go. Okay. So lectures, oh wow, did not come through very well. Super checks over some coursework, assignments, and video lectures. Because the lecture material in the fall 2020 website differs from the lectures recorded on YouTube, I have unioned them both. That should be fine. Seems like, yeah, it seems like it's like this. Okay. So let's just review that. So why parallelism, why efficiency, a modern multi-core processor, modern multi-core processor part 2 plus ISPC program abstractions, parallelizing code and example thought process, program optimization 1 and 2, locality, work distribution and scheduling, GPU architecture, and CUDA programming. Okay. Data parallel thinking, efficiently evaluating deep neural networks on GPUs, transformers, and CovNets, hardware specialization, programming systems for specialized hardware, mapping AI application to data center computer, domain-specific program systems and AI-driven performance optimization, cache coherence, implementing synchronization, memory consistency, midterm exam, fine-grained locking, lock-free programming, transactional memory 1 and 2. Okay. So most of this looks like it's duplicate in the lectures here. So let's do our union. How far along are we on the downloads? 13 of 19, so we'll let that go. I'm gonna copy everything from here to here, and we'll just zoom in here, paste that in here. Just format everything here, delete these unnecessary lines. Sure, I could have done a regex here to like clean this up a little bit faster, but the amount of time it takes you to write the regex, you can just do the manual manipulation as fast. Okay. So they have some naming issues here. There we go. That'll balance it out there. So let's do it from I to I here. paste that. Okay, I'm just doing this just to normalize the titles. Oh, we got an extra 2023 here. Or no, I forgot to do the I. There we go. I 2023 I. Okay, so what we can do here is do a little spacey space here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, everything's in order. So let's go ahead and delete all that. So Y parallel, so that's 1. So we can indent that. A modern core processor part 1. And then modern multi-core architecture part 2 plus ISP abstractions. This was renamed. But these 3 are good, so I'm gonna say, okay, bam. Oh, my phone's going off. I'll be right back. Okay, there we go. Alrighty, let's start diffing this. So these three seem very similar, so I'm just going to delete those and say that they're done. Optimization 1 and 2 work, distribution, scheduling, locality. This is called parallel programming basics in the lecture. This is called parallelizing code, an example thought process. I want like an emoji here to say that it was like different. Sorry. Different. Maybe we can do like a less than to say that there is a diff in that direction. And then these two, it looks like the video lecture has something on contention, but that should be in the one here. GPU architecture and CUDA programming is the same. Parallel thinking is the same. And then this is where we get into some differences here. So this is efficiently evaluating. That would be there. So this is a new one, distributed data parallel computing. And then that's going to be a direction that way. And it's new, so I'll put a plus as well. Distributed, and I'll put these in backticks just to make them obvious. And then we'll say down here key. Key will be on YouTube. This will be on course website. And then a plus will be actually, we'll just say it like this. Okay. Efficiently evaluating DNNs on GPUs. Okay, now we get into some other things here. Hardware specialization. Programming systems for specialized hardware. Mapping, and then if I look at the actual descriptions here, so he has one on cache coherence here. It's just out of order. So I'll delete that. So we'll indent that to say it's already there. And then we're at this, so we're at this location here. So memory consistency was what it's called. That's on implementing synchronization plus memory consistency. So I'm going to assume that that is this one here. Oh, and they pulled up hardware specialization there. Okay. Programming systems for specialized hardware. I don't see that here. And then obviously the midterm review lecture I don't need to necessarily do. Okay. Well, that one doesn't. So we'll indent that. It doesn't have a match. Mapping AI applications to data center computer doesn't have a match. Domain-specific programming systems and AI-driven performance optimization does not have a match. Cache coherence, we already had a match. Implementing, we found a match for that. Then it goes into fine-grain, so we have a match there. Oh, domain-specific programming would be this one. And then we have transactional memory. And then we have this one here. Okay, and this will be a okay. One, two, three. Let's go back here. So those things are taken care of. Parallelizing code. Optimization. Optimization 2. GPU. Data parallel thinking. Parallel computing using Spark. Yeah. Distributed data parallel think. Yeah, that one. Okay, we got that one. Hardware. So the cache coherence stuff comes later. Memory consistency comes later. Maybe what I do is I map the actual video links here. So we'll do something like video, and then we'll just paste the link in there. And that'll make it to where I can track this a little bit better. As far as like what videos match up to which slide decks on the website. Oops. And some of these are not going to have videos. Alright. So, what's the best way of getting at the video link? Would be share here. And then copy this. Paste it in here. And then we can delete this SI thing, pretty sure. Just be this here. Yeah, you don't need that SI thing. That's for the playlist, I think. Alright. So, share, copy, bang. Okay. Lecture 3. Share, copy. Bang. Okay. Parallelizing code, I think, is going to be the basics here. So that'll be share, copy here. Okay. Optimization 1, share, copy. Optimization 2. share copy. Okay. Alright, what's the next one here? GPU parallel computing, okay. Share copy. Data parallel thinking. Share copy. Distributed data parallel computing using Spark. Share copy. Efficiently evaluating deep neural nets. Oops. There we go. Then we switch up here to cache coherence. So I'm going to say share copy, but it's going to be this one down here. It's a little bit out of order on the cache coherence. Then memory consistency. Share copy. This one would be implementing synchronization and memory consistency. So that lecture video might not cover the implementing synchronization. So I'll add a little note here. Note, there might be a diff between slides and video recording on this one. Okay. So that was memory consistency. And then here we got fine-grained synchronization and lock-free programming, which would be this one here. And then here we go. Midterm review. Share copy. No class for midterm exam. Review. No. But their midterm review would be after implementing synchronization. It would be here. Midterm review. Yep. And let's paste that in there. Video. Domain specific programming languages. Share copy, which should be pulled up here. And then I'm going to copy his notes because it applies to this one too. Okay, maybe if we do this, it'd be a little bit better. A little tiny bit better. Okay, good. Okay. So it takes care of this domain-specific systems and AI-driven program optimization. Domain-specific programming systems and AI-driven, yeah. That was this lecture here. And then we got STM, or just transactional memory 1. So share copy, that'll be this one here. And then get transactional memory 2 on this one. Share, copy. Okay. And then hardware specialization, which is up here. Okay. So reordering, share, copy, hardware specialization. Okay. And then accessing memory plus course wrap up. Share, copy, be here. There we go. Oops. So if you look at video here, we're supposed to have 19. So we want YouTube 1, 2. Let me just write this out. Cat out readme. Grep for you. What are these? tu.be. And then word count line. It says 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19. Okay. It's definitely 19. But if you go back here, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1. So there's 2 more that don't have videos. These 2 here. They are slides only. So I'm going to do a slides link here. Slides. Everything should have slides, ideally. I have to go back to a previous version of the course to find them, but oops. Ideally, everything has slides. Oops. Oh, there we go. There we go. Oops. Okay. So now we go on to the website. We got to get all the slide links. So this one be here. Part 1. This could be part 2. I can close this out and this out because the downloads are done. So let's pull this down, go back here, and I actually do want to do it like, how do I want to do it? This guy over here, J? Yeah. Okay, so it's multicore 1 and 2. And then this thing. There we go. This one, program optimization 1. Be here. This one's program optimization 2. Will be here. This one is GPU architecture. CUDA. This one is data parallel thinking. This one is distributed data Spark. There's no slides on this Spark. Go to the next one. DNNs, this one here. Hardware specialization. Boom, 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 boom. Here? There we go. Okay, programming systems for specialized hardware. This one. Managing AI applications, data AI applications. And then domain specific program AI performance optimization. That goes there. Cache coherence. Here. This is implementing synchronization and memory consistency. Okay. This will be midterm review, which there is no slides for. Fine-grained locking and lock-free programming. This one here, which would belong here. Transactional memory, 1 and 2. Boom. And then accessing memory. Seems like they had a different wrap up from the previous ones. So let's hit J here. We're just going to go through all these. So Y, efficiency, those three, parallelizing code, optimization 1 and 2, GPU, data parallel thinking, distributed data. So the Spark video, I remember this video, I did watch this. I must have watched the CUDA stuff at some point. But I remember this was like a really not great lecture. Okay, and then a hardware specialization, programming systems for specialized hardware, mapping AI, domain-specific programming systems, cache coherence, implementing synchronization, memory consistency, midterm review, no slides on that one, fine-grained locking and lock-free programming, transactional memory 1 and 2, final exam. Okay. Odd that they can't distribute videos to the public this year. Programming assignments, we'll get those encoded here, but I do want to go to previous. Maybe if do. Oops. Can we do fall 24? Fall 23. There we go. Let me ask AI and just tell it, list all past versions of this course. Why are they all fall? Sorry. Why are they all fall? Do they not offer the course during other seasons? Okay, so they're all false, so I can just say, hey, oops, damn it. Hate it when I do that. I'm trying to close the AI and I accidentally closed the browser. Come on. Alright, let's go back here, fall 25. So we're gonna look for missing slides. So is anything missing? It would be 2 parentheses in a row. Okay, so distributed data parallel. So this is a Spark. So he does have it on fall 24. So let's grab that one. They took that out because, well, it's Spark. I know the professor has experience with Spark, but I don't think many people care about Spark. Isn't Spark like some type of distributed database? It looked very odd that Apache Spark open source distributed computing system design, fast in memory, big data processing, analytics, and machine learning. Yeah, it seemed kind of off that he would add that to this course. Notes. See note. This. Okay, and then we go back over here. What was the other one? There's 2 more, I think, right? Which are midterm review notes. Midterm. Sorry. Review. No. So that was that lecture, and then this lecture is accessing memory. They do not have there, so let's go back to 23. It should certainly be here. Review. No slides for that, so I'll just delete that. And then this is the accessing memory, which I've had I've been getting more experience, I should say, with methods of accessing DRAM. But I'm not really great at it quite yet. I understand more. I think I can approach this lecture now, whereas before I was very ignorant of like how DRAM is accessed. Okay, so that should be everything. Switch one more time. Okay, there's nothing there. All right, let's go to the assignments on fall 25. So we'll just do it like this. And we'll do programming assignments and written assignments. But we'll do them in, I actually feel like, okay. Let's just do, oops. Do that. Okay. Okay. We'll do that, and then that, and then that. And then we'll just copy these links here. And then we'll do the same thing here. Oh, that that happened. Well, we'll just do this one manually then. And then we'll do the rest of these like this. There we go. Alright, and this is going to be assignment 1. Oh, these are Git repos. Okay. Okay. So these are kind of like labs. Assignment 1, assignment 2, assignment 3, assignment 4, on Tranium 2, nice. Then assignment 5. Okay. Alright. That should be everything. Cool. Get init, get status. Okay. Get at all, get DC. Let's cat out our csapp.getIgnore. No, there's no getIgnore. Okay, good. Alright, so get status. We'll say get add all. Get DC. This theme is a little wonky because it's like yellow instead of green. So I think I might change my theme here. I kind of like this Everforest. It's not contrasty enough, but and then Groovebox I kind of like as well. Let's try that one. And if I scroll up here, I should be able to, yeah. Red should be red and green should be green. Let's change the background here though. I actually like these leaves a little better. Okay. Get status, get CI, we'll say add initial readme. And then we'll go over here, we're gonna go to GitHub. And then we'll add a new repository. And it's gonna be public, create repository. And we're gonna do this. Origin, yeah. Do that. Oh, let me go ahead and add my key here. Give me 1 second. Alright. Cool. Let's hit refresh on this. Should get my readme here. Great. Cool. And then I also want to push to Codeberg, so Codeberg sign in. I should already be signed in, right? Oh, I'll do that later. Actually, you know what? I should do that now. Let me grab my credentials. I don't know why it signed me out, but maybe they have a stricter login policy. What if I go like / here? Okay, I'm still not signed in. Okay. Give me 1 moment. I need to get signed in here. All right. All right. Sorry about that. Took me a while to figure out how to clear my clipboard history so I don't show my credentials. All right, so you push to origin master. So now over here, I'm just gonna say add new repository. The repository name is CS149, and we'll do master down here, create repo, and we're gonna do this, but we're not gonna do origin. We're gonna call it Codeberg. Git remote add Codeberg, and then origin do Codeberg. Git push all. Alright, looks like everything's on Codeberg now, so that's good. Alright, well, it is 1:23. Let's go ahead and get started on the first lecture and slides, which will be this one. And I downloaded everything, so I'm gonna re-enable my block on Google Video. Just to block that. Cool. Alright. And then we go over here. And CD into videos, CS. Yeah, where do we go to the videos? Okay. Stanford CS, okay. Okie dokie. Open up lecture 1, which will be Stanford parallel lecture 1. If I kill this, does it kill?
Welcome.
No,
my name is
maybe.
Kayvon. I'm a pretty casual guy, so Kayvon is a perfectly reasonable way to address me.
Hi, I'm Kunle. I'm the other instructor. You know, Kayvon's the software half. I'm the hardware guy.
Yeah, so I'll be doing a lot of the lectures at the front of the class, which are a little bit more software oriented, and then you get the A team in the back half of the class to tell you about how hardware really works. So. You're going to have, right now we have 9 TAs, you're going to have 10 or 11, so well, hopefully you get everybody pretty good support. Okay, so I'm a big person on motivation, so I thought that we would start by, okay, so first of all, I like to try and make lectures as interactive as I can for a big class like this. So one thing I'd like you to start is, why don't you just turn to your neighbor, who hopefully is a friend, or maybe not a friend, if you've never seen them before. You might be working through a few things with them today, so why don't you turn over, introduce yourself, say hi, suggest that you're a pleasant person to be around, and then one thing is, why don't you tell everybody why you are here? Okay, all right, so hopefully you've.
Great.
Very good job. Very good job. Okay, so here's a question for all of you. We have 270 people in this class, which is more than we've ever had before. It's always good to know why people got their butt up this morning and decided to take this class. You know, why are you here? This is actually a class where we have pretty different people showing up. We often have hardware architects, we have software programmers, we have people in machine learning that are tired of waiting for training to go. We have graphics folks. So who's here? Why are you here? Yes, sir. Sitting in the front, obviously.
So I did my undergrad and my most of my master's degree taking AI classes. Yeah, but I see feedback from people in the industry that you need to have
You code is
some-
slow.
Away from this class is that computers are a hell of a lot faster than they actually
And I think there could be no better class than this student class.
I think so. I think one of the things that I'd like people to take away from this class is that computers are a hell of a lot faster than they actually think they are. And so having, especially if you never built a system in your life, I'm not saying that you will, but for folks that are applications focused, I think that having a little bit of an intuition about how fast something should be is extremely important. Like when someone working for you goes, look, this computation's taking all day, you should be like, I mean, I kind of understand what that workload is. That should be a 5-second thing on 10 cores. Can really be helpful. Anyone else? Yes, sir?
Yeah, my mind is like hardware, there's software, and then what's going on in the middle to me.
Okay.
is
Yeah, that's great. So we are going to talk a lot about the interface between hardware and software. Typically, getting that interface right is step one to the key to performance a lot of times. Anybody else in the back? We got some machine learning interest. We have some hardware software boundary interests. Anybody else? Do we have any graphics folks here? Yes, ma'am.
I'm interested in everything.
Cool. I mean, graphics, like machine learning, has always been this field that's we got to get the algorithms right, but we also got to run really efficiently. So a lot of the technologies that we'll talk about have some genesis in graphics. So, okay. So some of the things that we're going to talk about. This is like actually, first of all, how many people have spawned a thread before in their life? And in what class did you spawn a thread for? 110. And you spawned a thread in 110 in the context of what? You're writing a thread pool.
So I don't see 110. It's 111. 107. That's operating systems. 110 does not exist here. But its prereq was what? $107. So it would have come after this. So you got math and physics, a little tiny bit of computer science, math, some engineering thing, more computer science, computer science, computer science.
Well, I actually forgot. You wrote the thread pool for what application, or was it just a generic thread pool?
It was just a piece of
Just a piece. Okay. So you didn't create a thread pool to actually have a concurrent application at all?
Yeah, I mean, we were trying to do like, it was like Stanford Farm or something like that, where we were trying to like run arbitrary, like prime number method and make words.
Okay. All right. So So you wrote a thread pool for exactly the reason on this slide, which is you.
CS1U, practical Unix. 2022. See if ChatGPT can find other courses. Find me all the courses available on this website. So there is computer graphics, rendering, geometry, and image. I think something wrong happened here because I remember this being a website. If we go to archive.org, put that in there. Yeah, let's go back to 2025 maybe. The last scrape was here. Let's take a look at it. Oh, it's still a test. Okay. Maybe we'll do it at the start of 2025. I could have sworn that I saw a page here. Okay, maybe not. Here? Nope. It's always been a test. Okay. Home maybe? Course info, lectures, readings. Hey, textbook. There's no required textbook. However, we find the following textbook helpful for architecture topics. However, in general, these days, there's plenty of great parallel computing resources available free on the web. Computer Architecture 6th edition, a quantitative approach. I don't think I want to do another computer architecture textbook. Yeah, I've seen this one before. It's very similar to CSAPP. C39. Kind of curious how they measure performance. They go into actual instrumentation or not. Page 39. They already get into registers, it's nice. Risk V. with improvements. I love these die shots. Well, I was looking for 39, I think. Just like performance. Yeah, here we go. Where does this go? Not the programming language, I take it. Is there a 7th edition? Yeah, it's 7th edition. That was published, end of last year. This would be a good one to pick up. Be more up to date. But again, it's focused on largely CPUs. I don't think it's going to be huge on GPUs here. Here you go, exercises. Okay. Wow, the paperback is $82. I've had this one recommended to me a number of times. Let's take a look at the index here. Sorry, read sample. Because I'm interested. It's the Kindle version. Yeah, I remember reading this. I wonder if I can just find the 7th edition PDF because I don't want to read the Kindle version. So this one I can get for 88 here. So it's a little bit cheaper, but the paperback is likely used. Yeah. So if I did buy new, it'd be $99 versus here I can get it new for $88. Here you go, table of contents. If I do GitHub here, what is this? Notes from the book, okay. Okay. Yeah, it's weird that there's only one commit here, or 3 commits. I guess he moved it over to here. Charles Fox. Is this other guy Charles Fox? Or is he just got some random repo they forked? Yeah, it looks like this guy's different. Different dude. Okay. He has a video lecture series. Oh, I can't view that because I blocked Google Video. Okay, I think I'm gonna take a break from looking into this book anymore. And he should have updated this to be 7th edition on his website here, because by the time this came out, they had already released the 7th edition. But yeah. I was looking for other courses that they offer to get a good idea for like what computer science courses there are at Stanford. '21 SI AI for Social Good. These are all like the basic things. Anything under 100 is super basic. Or stuff that's like social and economic. It's like, okay, I don't need to take that one. Minds and Machines, nah, it's more philosophy thing, psychology. Transformers, that'd be a nice one. Okay. That didn't go through. It's a pretty cool course website. I can't watch these. Oh shit, they got Zoom live streams for this. It's a pretty cool modern approach to a course. Having a Discord community, live streams on Zoom. And they're just like doing it as they're as they go. I'm gonna check this one out. That's a pretty cool course. Glad I found that. It also gives me a link here that I can go possibly to other courses. No. And then this is just gonna be whatever, right? Yeah, okay, great. Big ideas in cryptography, secure data, the presence of an adversary. I mean, this is one that I probably would do really well in. But it's stuff that I already know. CS40. See if they have a website. Duplicate. CS40. Oh, they got nothing. No bueno. There we go. This will be a fun one to do. I'll skip that. Alright, I'm gonna take a quick bio break. And then I'll be back in maybe about 5 minutes to resume the lecture here. Cool. Okay. Is this the whole book? Oh, okay. When was this one published? Yeah, 1997. Yeah, I'm not gonna be reading this. 98. Okay. Skip out of that. Just want to see what text these things require. None. Okay, that's enough of that. Let's get back onto the lecture.
In order to get stuff done faster. Makes sense. A number of you have probably also written thread pools for web programming or something like that before, right? Like, has anybody written like a web proxy or a little web server or something like that? A lot of the times we spawn threads to hide latency, to do something else. But in this class, we're going to be talking about multiple uses of why we're creating parallelism. And this class is, even though it's called parallel computing, we're going to talk about efficiency as much as we're going to talk about parallelism. And sometimes efficiency is a lot more important than parallelism. So I like to play a little game in the first day of class just to kind of make some things a little bit more explicit, at least while everybody's here. How would you to talk? How would you, that took 19 at the recording, right? And 10 one. Go for it. To do. There's like if you're getting hot and things like that, why don't you find set into the appropriate? Yeah. So you kind of had like an allocation problem. You also had a big data movement problem just to get everybody into the appropriate seats. So I actually think in hindsight that groups of 10 might have actually gotten people to a countable set a little bit quicker because you didn't have these dependencies to get everybody in rows. So I have a feeling that like if you're getting hot and things like that, why don't you file back to wherever you feel most comfortable. But thank you very much. So if I assume there's like 160 of you here right now, that was like only 10 times more work than we originally asked to do, for example, right? And so it shouldn't have been more than about 6 or 7 minutes to add it all up sequentially. It should have been much less because now it's just +1. It's not adding a harder number. But we were nowhere close to that, right? Like in terms of a 100x speed up over the sequential algorithm. And it was largely because of the cost of communication, synchronization, moving all of you. And so this is something I want you to keep in mind because although the class is about parallelism, I mean, the reality is that it's really about moving things around. Like every system that I think I've ever built, I bet Kume probably would agree, is kind of the only thing that really matters is communicating and moving stuff around. Okay, so let me get into just some summary and some logistics real quick. Theme number 1 of this course is we're going to get you thinking kind of like you were just thinking now. Like we're going to give you problems. You need to compute this problem, and you need to do it as efficiently as possible. And so we're going to want you thinking about how to decompose things in parallel and how to synchronize. And we're going to, I like that there's some folks interested in the hardware-software boundary because we're going to talk about programming mechanisms that help you organize that thinking, that make it a little bit easier to solve problems like this. Now, some of you are computer.
I skipped over the demos because they're in-class activity, and I've already watched the lecture at least 2 times already. Okay, so one major motivation to use parallel processing to achieve speed up, figuring problem speed up using P processors, execution time of one processor divided by execution time using P processors. But that's assuming that the entire problem can be sped up or can be parallelized. Class observation from demo 1, communication limited the maximum speed up achieved. In the demo, the communication was telling each other the partial sums, minimizing the cost of communication, improving speed up, move student processors close together or let them shout. Imbalance in work assignment limited speed ups. Some students' processors ran out of work to do when idle. Others were still working on their assigned tasks. Improving the distribution of work, improve speed up. Massively parallel execution. The problem I just gave has a significant amount of communication compared to computation. Communication costs can dominate parallel computation, severely limiting speed up. Course 1 theme, designing and writing parallel programs at scale. Parallel thinking, decomposing work into pieces that can safely be performed in parallel. Assigning work to processors, managing communication synchronization between the processors so that that it does not limit speed up. Abstractions and mechanisms for performing the above tasks. Write code in popular programming languages.
Your day jobs, or you write software. Some of you are EE and design hardware. Another aspect of this course in the room. Another aspect of.
Can I jack the volume up on this thing? Doesn't appear I can. Okay.
About the fundamentals of how hardware works, because you can't make things go fast if you don't know how things are running. Hardware, you write software mechanisms. We're gonna give you real quick. Theme number 1 of this course is we're gonna get you thinking kind of like you were just thinking now. Like, we're gonna give you problems. You need to compute this problem, and you need to do it as efficiently as possible. And so we're gonna want you thinking about how to decompose things in parallel and how to synchronize. And I like that there's some folks interested in the hardware-software boundary, because we're gonna talk about programming mechanisms that help you organize that thinking, that make it a little bit easier to solve problems like this. Now, some of you are computer scientists, your day jobs, or you write software. Some of you are EE and design hardware. Another aspect of this course is about the fundamentals of how hardware works.
Parallel computer hardware implementation, how parallel computers work, mechanisms used to implement abstractions efficiently, performance characteristics of implementations, design trade-offs, performance versus convenience versus cost. Why do I need to know about hardware? Because the characteristics of the machine really matter. Recall speed of communication issues in earlier demos, because you care about efficiency and performance. You're writing parallel programs after all.
Things go fast if you don't know how things are running under the hood. So the hardware is a little bit about why code has to be structured in certain ways in order to run fast. So software people, hardware designers need to know about hardware because they like to build this stuff. Software folks need to know a little bit about hardware to go, wait a minute, why am I making my program structured this way? It seems hard or it seems difficult. Why can't I write it in another way? And more so than in previous years, there's going to be a stronger component in this class of actually designing hardware itself. So there may be an extra credit assignment at the end of the quarter where you can actually make a piece of hardware on an FPGA or some programmable substrate. And then the last thing I want to just really emphasize is I care a lot about teaching people about efficiency. In some cases, like in this exercise where we added up the number of people in the room, if it would have been easier for one person just to scan the rows and add them all up, that's great. That's a faster, potentially more efficient solution than a solution that was highly parallel but had a lot of communication.
So fast not equal to efficient. Just because your program runs faster on a parallel computer, it does not mean it is using the hardware efficiently. Is 2x speed up on a computer with 10 processors a good result?
Not get too hung up on parallelism, because efficiency is often what matters. So here's an example. Imagine that you go off to your next internship or full-time job or whatever, and you were asked to write, to speed up a program on a 10-core processor, something like that. And you came back a month later, and you were able to get 2x speed up. You went to your boss, you said, look, it's 2 times faster. Do you get fired, or do you get a raise? Okay, so we have a very negative class. Some people want to fire you. What's a rationale for getting fired?
I mean, you had 10 processes, but all you could achieve was a 2x speed up.
You had 10 processors, you only got 2x out of it. Maybe you're using those processors very inefficiently. They say, you're fired, go back, take CS149. Any reason to give the person a raise? Yes, sir?
The
Yeah.
workload
Yeah.
could be here.
I'm just saying not all programs are like so easily parallelized.
Like the one we just did, right? Like that's a pretty hard program to parallelize. Is there a reason why you might be satisfied with 2x?
Yeah, if the performance gains by that offset the additional cost of using a 10 processor computer.
Yeah, like maybe computers are cheap and like being able to reduce the response time of your website by a factor of 2 translates into a ton of sales. You might be really happy. Or like Google search results have to be returned in a certain amount of time, otherwise people lose interest and go somewhere else. Another example, imagine you had a computer game that ran at 15 frames per second in a game, and you made it get to 30 frames per second. That might be the difference between the game shipping or not shipping, right? So sometimes we care about raw performance. Sometimes we care about efficiency. Ideally, we'd like to have both. Okay. Okay. Yeah, and hardware designers care a lot about efficiency because they're like, the more hardware we put into the chip, the more expensive this chip is going to be to manufacture. So I'd like to put in the minimal amount of hardware that I can get by with and still meet my performance goals. Okay. All right, middle of the lecture, let's take a breather for a second and just go through some logistics. This would be a good time to act. Here's the website. All the lectures are posted, so we try and make sure that your lecture slides are posted prior to lectures so you can follow along while you're in the classroom. Notice that there's a mechanism to comment under the slides. So you can add a comment. And typically, the reason why we do this under the slides is you can ask an actual question specific to the slide. So like intellectual questions, like I didn't understand this, can someone explain multi-threading? Very much prefer them to come in via the slides so that other people can see them and respond, as opposed to making those on Ed. Ed is for like logistics and stuff like that to me. And you can always go up here to the course feed and see all the comments that people have made. Okay, back to my lectures. So that's that. There's no textbook. The slides are basically the textbook. The internet is full of great resources, and so a great way to make a helpful comment would be to say, hey, I actually learned it from this website. The explanation in class was pretty bogus. This is way better. Go read this, right? All right, so you're going to be doing 4 programming assignments. It's the bulk of the grade. The first programming assignment will come out on Thursday. It's a little shorter. The next 3 are significantly longer. You will be writing a much more elaborate version of a thread pool where we give you dependencies and everything.
So it looks like these change. Assignment 1, ISPC programming with multi-core CPUs. Assignment 2, schedule a task graph. Schedule 3, write a renderer in CUDA on NVIDIA GPUs. Assignment 4, optimizing deep neural network computations on an AI accelerator. Change from Chat 149 flash attention transformers for a mini language model. So they flesh this out. Chapter 5, write the world's fastest CUDA kernels. So these are skills that I will, that I feel are in demand right now. And that's probably why they're putting them in the latest version of the course. Programming assignments can optionally be done with a partner. We realize finding a partner can be stressful. Fill out our partner request form by okay, just logistics things.
Render yourself that will make pretty pictures via in CUDA as fast as you can. Not made yet, but intended to do so. Assignment 4 is definitely very new this year. You're going to implement the transformer module of a DNN, and you're going to try and do it as fast as possible so that you can have a chatbot kick out tokens, and maybe we'll have all the chatbots chat with each other or something like that. Okay, so there's 4 assignments. Typically after Thanksgiving, we release a 5th, which means you can use the 5th because it's awesome and fun.
So I think that is the, go back here, I think that's the, where's that? Yeah, Tranium. accelerator. It is really weird, these slides don't line up. ISPC program multi-core. So assignment 4 here is the Tranium 2. Should be this one. That's probably a Tranium chip there. Yeah. So that's why they put the Tranium PCB and chip there. And 5, write the world's fastest CUDA kernels. Okay, looking forward to doing these.
The score of one of those by a few points, usually about 10 or 15 points. Okay, most of your grade is there. We do written assignments that are graded on a did you make a reasonable effort. The written assignments are all previous year's exam problems. So about every 2 weeks there'll be a written assignment plus practice problems. So we distribute practice problems throughout the quarter. You can think about this as a participation grade, largely. And then the last part of your participation grade is I do not want people studying for the final exam and not thinking at all about the course between now and the final or the midterm exam. So just to force you a little bit to engage with week as the lectures, we require one reasonable comment per lecture, approximately, in approximately the same week as the lecture. So no hard rules on this. But I hope that you average about 2 comments per lecture throughout the quarter. And if you really like a lecture and want to do a bunch of comments on one lecture and skip the next lecture that week, that's fine. You can kind of see some of the, and so we expect you to do that. And I think good architects typically write well. Write clearly, not elegant English language prose, but as an architect, you're constantly communicating to other people about technical things, and I think that...
Okay, 17 lectures. Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Counted 18. Maybe this is because it's part 1 and 2, but these are part 1 and 2 as well. Maybe it's at the start of the course and they ended up splitting them out. Something like that.
So you can take this offline, but here are some examples of fodder for comments. In a big class like this, the comments actually works pretty well because somebody asks a question and then other people answer it. Don't worry if someone has already answered the question, you could answer it again. The 8% last year, about 10% of the grade. Okay. The only last thing I wanted to say now, last year, about 10% of the grade. Okay. The only last thing I wanted to say now is we do most people called asking. I mean, some of the time I'm going to say.
Could you indicate like which question or which component will be completed after which lecture?
Sure. Yeah, I could even do that in lecture. I mean, it's not super modular like that, actually, so it might be a little hard. But in general, the programming assignments, with the exception of assignment 1, all the content, I believe, is released prior to all the lecture content exists prior to the assignment coming out. In assignment 1, you'll have, conceptually everything you need on Thursday, and logistically, with a little bit of programming example, comes next Tuesday. But yeah, yes.
Will the final exam be in person? Or
Final exams in person at the university slot. That is the one thing that we are a little bit strict on. it is hard to run asynchronous like that. Sure. It's perfectly fine. Last 20. Okay. All right, so keep going. All right. So the last 20 minutes here, 25 minutes, maybe let's go into a little bit more technical material that is perfectly fine if it's new to you, but some of it may be stuff that you have seen. So I like to set the stage for tomorrow or Thursday's lecture. Okay, so sometimes it's kind of useful to think historically about things. And when I was approximately sitting in classes like this, and I was really interested in parallel computing, I actually had professors tell me, why are you interested in parallel computing? Just wait a year for processors to get faster. Right? And so this is a very old plot that Kunle made more than almost 20 years ago now, of processor performance as a function of time. Okay? And it's a log plot, so you see the exponential. And so you just waited, and Intel would ship their next CPU, and next year it would run your program faster. So you spent all this time taking CS149, you got some skills, and then all of a sudden, like, your parallel program had to now be even faster to improve over the sequential program. And do you know why that was the case? Like, if we, maybe some of the hardware architects in the room? Yes, sir.
Transistor sizes getting smaller.
Transistor sizes were getting smaller, but that's not a direct translation to performance. So you're correct, but you took a couple steps.
Could increase frequency without driving power.
So transistor sizes getting smaller allowed for a couple of things. It allowed for them to be clocked higher, so frequency could go up. It also meant that more transistors could go on the chip, and architects had to have clever ways to use those transistors to translate into performance. Okay? And in this class, I'm oversimplifying a little bit, but you can kind of think about two major reasons as parallelizing your code for you without you ever knowing it, and two, increasing CPU clock frequency. So this is where I get to a few questions that may seem really dumb, but one of the reasons why I like people writing comments is sometimes when you sit down to write something, you realize that your thinking is not as precise as it may seem. So, look to your left or right, and I want you to spend 30 seconds answering this question. What is a computer program? And just really a program from the perspective of a computer. Here's definitely a program written in C. No problem. This is a computer program. But from the perspective of a computer, what is this? What is a program? And just go ahead and give that a shot. Like spend 45 seconds. What is a program? Can you define it yourself? All right. So someone who hasn't said anything yet, if a talk show host found you on the street while you're walking around San Francisco and they said, "What is a computer program?" You're on camera. What might you say? I just want to see some new hands. New hands. What is a computer program?
A piece of text that can be translated to hardware instructions.
A piece of text. That's a piece of text. That can be translated into hardware instructions. And I think that the text aspect doesn't really matter too much. What's important is the back half of your comment is a program is just a list of instructions. Right? So if I take this program, it certainly has a meaning. It has some semantics, and a compiler might get to it. And at the end of the day, whether or not it's a compiler or interpreter doesn't matter, but at the end of the day, a computing machine runs a list of instructions. So here are some examples of x86 instructions that you might have seen. So in CS1, 11, now like folks, so 7, you've looked at a bit of assembly. This is x86. Most, if you have an Apple laptop these days, it would be ARM assembly. But at the end of the day, all a computer does is it gets a list of commands, and it executes those commands. So it's kind of like me making carne asada, which I have to make tomorrow night because I'm up for dinner. I get a list of instructions. I have a set of commands, and maybe another way to ask this question is, what does a processor do? So I'll throw it back at you, talk it over for a second. if I asked you and I said, like, what does a processor do? If a program is a list of instructions, what does a processor do? I'll let you talk it over for a second. To execute those instructions. For those of you that just said executes the instructions, which is a perfect first answer, my follow-up is, what does it mean to execute those instructions? What does executing an instruction do? Okay, let's talk about this. So I heard a lot of people immediately say a processor executes instructions, which is exactly where I wanted you to think about it. And now let's dive a little bit deeper. What does it mean to execute an instruction? What does executing an instruction do?
Either performing a computation in ALU.
Okay, so it performs some math, like what you did when you came up here. Okay.
Or jump somewhere else in the program set.
Okay, or it jumps somewhere else. Okay. Anybody want to add? I think I can't disagree with any of those. Those are two examples of instructions. Changes a register's value. What are other things instructions might do?
Access memory.
Might read or write to memory. So at the end of the day, we can boil all of this down to instructions perform some operation, like arithmetic or math, and the result of those operations is a change in state. And what I mean by state is either values in memory or values in processor registers. So if I go back, let's look at this instruction sequence here. Oops. Oh, there it was. You see some instructions which are referencing registers, and like moving a value from one register to another is changing the value of the target register. There's other instructions in there when you see the parens. Those are accessing memory at certain addresses and stuff like that. So what I want you to think about, this is a diagram I'm going to use heavily throughout the rest of this lecture and the next lecture. And this is a really cartoon diagram of how to think about a processor. But for most software people, this is pretty sufficient. I like to think about three pieces of blocks in any modern processor. One of them, which I'm always going to color orange throughout this class, is about control. Figuring out, like, it's managing where we are in the instruction stream and figuring out, once I get the next instruction, what do I do? Then I have this yellow box, which is responsible for the arithmetic, maybe adding some numbers or carrying out a move or multiplying some numbers. And I'm always going to call that yellow. And then I have stuff that's blue that's state. And I'm calling this the execution context. It's the context in which we run a program, which is just a big set of values of bindings from register 1 has this value, register 2 has this value, as well as memory has all these values. And the simplest possible way to think about a processor is it determines, given where we are in the program, where we are in the recipe, what to do next. It grabs the appropriate values from registers, it performs some math, and then it updates the value. For example, if I have a simple instruction like add the contents of R0 and R1 and put the result in R0, well, that processor will reference the two, R0 and R1. See how it's in red here? It will do the math. It will compute what? Yes, and what is that? Compute 96, and then it will update the value of, so it gets the contents of those registers, it updates the value, and then it modifies the state of the program to 96. Very, very simple instruction, add. And so for now, I want you to think about this processor as every single clock tick. It's just grabbing the next instruction, executing it, and updating registers. That's all it's doing. Okay? So my review here is hopefully this is review from 107 or 111, is what is a computer program? It's just a list of instructions. What are instructions? They are commands. They are operations to the processor. And those operations are about performing arithmetic or modifying state. And when we talk about state, I'm talking about the values of data in registers or in memory. Okay, there's a question?
You answered it.
Okay, cool. Right? So this program has 5 instructions in it. So it will take 5 steps, 5 processor clocks to execute it. Make sense? Is there any way we could do better?
You can do the multiplications in parallel. Because
What
R0
if
or
I had
1
2
are completely
processors?
separate, and R2
Okay?
separate.
This is your program. This is what, let's say I'm a computer and you hand me this program to run. what does this program mean? This program says you must do instruction 1, then you must do instruction 2, 3, 4, 5. That's the order. If I like trying to make my carne asada and I do things out of order, I will be unhappy with the results, right? So the meaning of this program is that the results have to be such that we did these things in this order. But what if we had 2 processors? Yeah.
Do you want to multiply steps in parallel and not the add steps in parallel?
Yeah, so
Or maybe not the add steps.
looking at this and you're realizing that like this multiplication only depends on register 0. This one only depends on this value R1. So, you know, maybe if I wanted to assign work to processors, I could do something like this. Right? And now what can I do next? You know, 3 can go where?
Either side.
Actually, it can go anywhere, right? I'll even put it here because I like processor 2 better. And then what?
Add.
Can I do better?
It can go up.
Right? Because this only depends on 1 and 2. So we can do, and then 5 has to come after 4 and 3. So it's possible for me to do better, even if, you know, even if I have a program that looks sequential because it's written in a line. If you look carefully at it, there's some parallelism there. So the first major, and by the way, like you notice what I'm saying is the program says, here's the program. You better compute results that are the same as if you ran them in the order that I told you. But if you run them in a different order and I can't tell the difference, then it's okay. And that's a really big difference. This program that I have right here is a sequential program. I have written this program which says the output that I want is as if you did this, and then this, and then this, and then this. I didn't think about parallelism at all when I wrote my program. But I wrote a program where someone can muck with the order, in particular make it parallel, and I'd get the same result. I would never know. But my program would be faster. Right? So like, for example, what if we had 3 processors? Could we do better? Well, before, what did I do? I did it in 3 cycles. If we have 3 processors, how long would it take? Are you sure? Why 3? Well, I can definitely parallelize the first 3 operations, all I want, but I have a chain of dependencies that keeps things 3 cycles. Yes, sir?
So doesn't each processor have its own, like, in this example, like, its own
I'm speaking very abstractly right now. Just imagine that like we
execution
have the
units
ability to
and
execute 3
updated
things at
slides.
once, and I'll come back to that in
Is
one
that
second.
comment right
Good
there?
question. Right? So conceptually, when I look at my program, and that instruction sequence that I gave you, actually, I'm just rewriting it now as something that may be a lot more familiar, like a dot product between 2, 3 vectors, key machine learning operation. These are the true dependencies, and this program has different amounts of parallelism at different points. Okay? So this gets to key idea number 1 today, or well, we've had a few key ideas today, but it gets to the reason why more transistors did translate into more performance, which is processor architects were designing hardware that were looking at the programs that you gave it and said, they didn't do any parallelism, but hey, look what I found. I happen to have multiple instruction units that I can do multiple things at once. I will go find it, and I will reorder the program to be parallel for you without looking, you know, without you ever knowing. And so to your question about registers and stuff, really what I mean here is we've replicated, you know, we still have 1 core, but we have 2 execution units and ability to execute 2 instructions per clock now. And I added this out-of-order control logic box just to say that now there's some smarts on the processor to figure out what's going on. And if we look back like 20 years, you look like for a simple Pentium 4 processor, this is a diagram from a long, long time ago, and I draw my color scheme on it, it's not all that different from my little cartoon. They have the ability to...
Okay, so superscalar process execution. I'm going to ask AI, or actually no, I'll ask Gemini, because Gemini's been outperforming ChatGPT on this. So what is the difference between superscalar execution and instruction level parallelism? Is the overall potential to execute multiple instructions simultaneously, while superscalar execution is a specific hardware technique used in multiple execution units pipelines to realize that parallelism. So instruction level parallelism is the inherent parallelism of the workload, and then superscalar execution is how you realize that parallelism in hardware. Where is this star coming from? Or the compiler finds independent instructions at compile time and explicitly encodes dependencies in the compiled binary. No asterisk on this slide. Oh, up here. Processor automatically finds independent instructions, or the compiler finds independent instructions at compile time. Okay. Superscalar processor can decode and execute up to 2 instructions per clock. And this is where superscalar processors, I guess my mental model for the actual design of these processor cores, I guess you would say, isn't really strong. Because I've always viewed it as like, this exec layer isn't as simple as it is in this diagram. Like there's all these different functional units, like a division functional unit, a multiplication, you know, there's not just one ALU, there's like all these different units, functional units that can do different things, do load stores. But I guess in front of all that, he's saying you have this out of order control logic and then fetch decode units. This would be a hyper-threaded, a SMT, symmetric multithreading core, because there's 2 separate fetch decodes. And then of course you have caches in front of this, not only L1 to L3, but you have the TLB cache, you have like all this stuff. I guess TLB cache would be on the MMU, but in here you'd have an instruction cache, which is separate from the L1. So you'd have a bunch of different caches in front of the fetch decode and the load store functional units. Execution context is a multi-dimensional register file with a whole lot of different state. Yeah. So it's obviously a very simple diagram here. Okay, they said side on old Pentium 4 CPU. Yeah, this is a little bit more realistic here. So, and this is old Pentium 4. Wow, that's quite old. Let's see here. Yeah, execution unit has all these different functional units. So SIMD, floating point unit, FPU, integer unit, memory interface unit. So that'd be load and stores, and they'll have multiples of all this stuff. Retirement unit, reorder buffer instruction pool, retirement register file. So here we go, instruction fetch unit, and then here's the L1 instruction cache, which is separate from the data cache over here. So yeah, the diagram that I was kind of explaining was already on this slide here. So we get our instructions fetched. We then decode. Simple instruction decoder, complex instruction decoder. Okay. Microcode instruction sequencer. Register alias table. This is probably because there's probably like a level indirection here because of speculative execution. That's my guess. Retirement unit, reorder buffer, instruction pool. Okay. Internal data result buses. Go to data cache L1, which goes out to the memory bus, L2 cache and L3 cache, main memory. Memory reorder buffer. Okay. Next instruction pointer unit. Branch target buffer from integer unit. Okay.
4 different instructions at the same time.
Oh, interesting. They have a little. Can I select this text? No, I cannot. But I can type it in. So ixbtlabs.com articles pentium4 index.html. Is it still online? We will find out. ixbtlabs.com articles pentium4 index.html. Looks like it's not responding. Let's go to archive.org. Paste that in there. And wait a minute. Here we go. Looks like that's not going to load. It's just a little blog post with a diagram here. Computer hardware in detail. Can I just visit this website? Or is it down? Looks like it might have went down this year. So this was in April 16th. That was just recently. I mean, they don't have any recent posts here. You might just pick this off of Google image search, and I'm just like wasting my time reading this, but it's a short little article. Might be worth reading. Let's get back to the slides here. Here we go.
Or 3 instructions at the same time with a variety of units. And real programs are a lot more complex. Here's a longer instruction sequence. A good thing to do on your own is to kind of verify that this is the dependency graph for that instruction stream. And that dependency graph is limiting the total amount of parallelism that you could ever find with this technique of automatically parallelizing within a single processor without you ever knowing it. Yes?
What would we look up for teaching to understand better how that actually happens in the processor?
Well, superscalar execution is the first one. And then you need a good reordering algorithm. You could start with Tomasulu's or something like that. I don't know if these days if that's the best.
To understand
parallelizing within a single processor without you ever knowing it. Yes?
What would we look up for teaching to understand better how that actually happens in the processor?
Well, superscalar execution is the first one. And then you need a good reordering algorithm. You could start with Tomasulu's or something like that. I don't know if these days if that's the best.
I mean, basically out of order execution is the key.
Yeah, go to Hennessy and Patterson, read the out of order execution channel, and then you're well prepared for EE280. These days if that's the best.
I mean, Basically, out of order execution is the key.
Yeah, go to Hennessy and Patterson, read the out of order execution channel, and then you're.
So that is the. This book is just so well referenced. I might just buy it, just to have it. So he said something about our.
Basically, out of order execution is the key.
Yeah, go to Hennessy and Patterson, read the out of order execution channel, and then you're well prepared for EE.
So instruction level parallelism should have out of order, right? There is no out of order section, but there's a section on instruction level parallelism. Might just buy this book just to have it.
But there's a problem. Remember when I said if we had the ability to do 3 things at once, we ended up in the same performance as 2 things at once? That's because if I write just like a sequence of instructions, there kind of usually is fundamentally an order to it, right? And so folks studied, here at Stanford, actually, in the early days of parallel computing, they did a lot of studies of how much parallelism could we automatically extract if we asked the programmer to do nothing and we found what parallelism exists in their program. And they found that the x-axis.
Most available instruction level parallelism is exploited by processors capable of issuing 4 instructions per clock. Little performance benefit from building a processor that can issue more. Instruction issue capability of processor instructions per clock. And that's just because of the workload. Could you have I guess theoretically you could have a workload that does perform better, but it's probably not a realistic workload, I guess.
Operations this processor could do at the same time, and the y-axis is the speed up. And they found that once you build about 3 or 4 operations at the same time into your processor, if you start building more, you can't use them because programs don't have that parallelism. Okay? So all of a sudden they could stop. They couldn't play this trick for you anymore to speed things up. Okay. All right. So here's a graph that you probably would have seen. Again, it's x-axis as it's a fancier version of Kuhnle's old graph. X-axis is performance. X-axis is time, and the y-axis is actually transistors, not performance. It's transistors per chip. And in general, okay, now we're starting to fall off of it for the last 5 years or so. But in general, we've been able to shrink transistors for pretty reliably for up until very recent times. Like more and more transistors. Like a modern NVIDIA chip has something like, I think 100 billion transistors on it. I think it's like 85 billion was the last one. So, but we can't turn those transistors into more execution units because we know we can only do about 3 of those things. So that's sort of this green line. This green line is transistors per chip. The purple line.
This is a really important diagram I should commit to memory here. So no further benefit from instruction level parallelism in the past several decades since I've been alive. So that's just baked into design now. It's like you have 3 or 4 parallel execution units, I guess you would say, which isn't really true. What I've learned in CSAPP is that you have all these different functional units, and your workloads can exploit the functional units in different ways. Power, we can't push any more power. So instruction level parallel, this is just inherent nature of the workloads that we run, is that they CPU bound workloads, generally the programs that we express in languages like C and other languages that are like in that ancestry, is that they don't have a lot of inherent instruction level parallelism. So that's just the nature of the beast. Like, we were able to get that boost, but we can't get any boost from just instruction level parallelism anymore. The power curve here is due to the more power you put into the chip. I guess power and clock frequency are tied together in that if we increase the clock frequency more from, and this is around like 2000 was when this started happening. If we increase the clock frequency any more, it's funny this graph ends in 2010. I'd like to see how it continues. We would have to put more power into the chip, and the more power you put in the chip, the more heat it generates, the more wattage it draws, and it's just massively power inefficient. So it's a power efficiency thing. You need a lot more infrastructure for cooling the chip to keep it from overheating. Just a lot more issues with putting more power into the chip. So power and clock frequency, I think, are tied, but the actual amount of transistors on the chip has increased, and we've used multi-core to leverage the additional area that we have from that.
Operations per clock, and they stopped adding operations per clock because it didn't help anymore. Now the dark blue line, correlate both blue lines are actually, they were increasing clock speed, like 500 megahertz, 750 megahertz, gigahertz, 2 gigahertz, 4 gigahertz. And that's what really stopped moving about 15 years ago, right? And for the architects in the room, do you have an idea why clock frequency stopped? Yep. Because of power, right? So we couldn't turn more transistors into free parallelism, and we couldn't make your instruction stream go faster because we couldn't increase the frequency of the machine, right? And that's completely power driven. Like, these processors that you see today are non-trivial. Like, if you take an RTX 4090 GPU and you take the
so the power wall, power consumed by a transistor, dynamic power, capacitive load, is this like approximately equals? Is that what that is? I'm not familiar with that symbol. I wish I could copy it. Dynamic power is approximately capacitive load times the voltage squared times frequency. Static power, transistors burns power even when inactive due to leakage. High power equals high heat. Power is a critical design constraint on modern processors. TDP. What does TDP stand for again? TDP stands for what? Thermal design power. Thermal design power, also known as thermal design point, is the maximum amount of heat that a computer component, CPU, GPU, or system on a chip can generate, and that its cooling system is designed to dissipate during normal operations at a non-turbo clock base frequency. Some sources state that the peak power rating for a microprocessor is usually 1.5 times the TDP rating. Graphics processor units are known to have even larger discrepancies between peak and TDP. So there's measured in watts, but it's an amount of heat. Is watt a unit of heat? In physics, is watt a unit of heat? No, watt is not a unit of heat. It's a unit of power. Heat is energy. Heat is not power. Heat is measured in joules. Power is joules per second. So I guess you can just say multiply by seconds. That you run it. me go back here. So watt is a joules per second. Joule is a unit of energy, which is unit of heat. Okay. Maximum amount of heat per second, I guess you'd say, that a computer component can generate. So it is output. It's not a draw. I've always used this wattage as electrical watts, like draw. But it's actually, and I guess these should be equivalent, relatively equivalent, is the waste heat should equal the draw, right? Because it's conservation of energy. All right, so there's dynamic power, and then there's static power. Transistors burn. We already talked about that. So these are TDBs. M1 laptop 13 watts. It's a Core i9. Desktop CPU is 95 watts. NVIDIA RTX 4090 GPU is 450 watts, but it has a big heatsink and fan and cooling system. Mobile phone processor is half to 2 watts. You don't want your phone heating up. And it has to passively cool the processor by dissipating heat into your butt. Most fast supercomputer is in the megawatts. Okay. Standard microwave oven is 900 watts.
A microwave in my kitchen, you are within a factor of 2 of running that thing, you know, in a machine learning workload at full tilt versus microwaving your yesterday's hamburger. You are in the same ballpark of energy being spent. And that energy translates into heat. Heat translates into the need to cool that thing. And so you just cannot continue to increase frequency. And we'll talk a little bit more about that. But a nice rule of thumb is that power is going to go as the square of frequency. So x-axis here is clock speed. Y-axis is power consumption. So it's a very inefficient way to go faster is to try and increase that clock. Okay? So this is where we were not so long ago, you know, when I was in grad school.
So this is interesting. Power draw is a function of clock frequency. Dynamic power, core voltage. It's determined by its voltage. It's the square of the voltage, not the square of the frequency. Why is this also... Shouldn't it have a linear, since the square isn't on the frequency, shouldn't it have a linear relationship to the frequency? So say the voltage is constant, the load is constant, and you just increase the frequency. That's a coefficient. That's not a power there. Good old non-tech. Let's pull that guy open here. Is he still kicking it? forums.anandtech.com show thread.php !t is equal to 228.1195. Yeah, I thought he shut down. Unless it's HPS. No. Archive. Oops. Yeah, I think he got bought out, right? Like, if I remember correctly. I imagine he was still kicking it here, yeah. Okay, file not found. Go back here, maybe? How old are these slides? Still nothing. Did I get their URL right? Forums anontech.com show thread the PHP T2281195. Well, let's go all the way back here, see if it's there. Hey! The hell? Oh wow. I guess they're still kicking it. So then why is this not a thread? Because show thread. So this is a thread ID here. If I go here and just go to a thread, some random thread here. Hey! This is just SEO garbage. It gets automatically filled in there. Images are broken. This is posted when? 2012. So changed his avatar. No, his avatar's missing. This guy did. Alright, I will read that later. Put it on my reading list along with all these other things. But the general idea is that as you increase your clock frequency, the square, the power consumption is increased by a square.
And the only way to use all these transistors. So this is where we very inefficient way to go faster is to try and increase that clock. Okay, so this is where we were not so long ago. You know, when I was in grad school, software. All of a sudden, the only way to use all these transistors would be I, as the programmer, have to tell the processor, here are two things we can do at once. Now, luckily, in machine learning and computer graphics and image processing and photography, that's going to be pretty easy. And so that's when people started building processors with chips with a bunch of processors in it, where they took that one single instruction stream and allowed for more and more things to go in parallel. So one of the things you're going to do in this class starting on Thursday is the first thing is you're going to go, wow, if I actually just write code properly on a machine that you're used to, like a laptop or the quad-core Myth machines, the difference between C++ code, you know, compiled C++, I'm not talking about Python or Lua or anything like that, compiled C++ and well-written, properly parallelized C++ is about 30 to 40x on your laptop, even with 4 cores. So we'll talk about why that's the case next time, right? And you're just seeing some big chips out there. Like you can go buy an AMD chip these days with 64 cores in it. We'll talk in the class about how NVIDIA processors are more of the same thing, just different point in the design space. There's 18,000 floating point multipliers on a 4090. So that's a lot of parallelism you have to have in order to use this thing. If you look at how many cores are there in the world's largest supercomputers today. These are megawatts. These are basically power draws of small towns. And we're in the orders of hundreds of thousands of CPU cores. This is not just a big iron thing. Go crack open your iPhone or go crack open your favorite Android phone. You'll find multi-core processing, both CPU and GPU. If you're working embedded, you'll find multi-core processing. All right. So far we've been talking about parallelism and communication and stuff like that. In this class,
Is a Raspberry Pi considered a embedded system? Always viewed like embedded as being like microcontrollers. Like if you can run an operating system like Linux on it, I don't really consider that embedded, but maybe I'm wrong.
you got to be efficient. And one thing we're going to talk about in multiple lectures this year is how the architects of the world are saying we are not going to, if we have to be more efficient, we cannot provide you general purpose cores. We're going to have to provide you much more specialized cores that do specific tasks.
Okay, he's got some extra slides here on mobile computing, or all computing, I should say. What is a big concern in all computing, but mobile computing especially, is power usage. 2 reasons to save power: run at high performance for a fixed amount of time. 2 reasons to save power: run at higher performance for a fixed amount of time, run at sufficient performance for a longer amount of time. So power is equal to heat. Chip gets too hot, it must be clocked down to cool off. Another reason hotter systems cost more to cool. Power is equal to battery. Longer battery life is a desirable feature in mobile devices. Mobile phone example: iPhone 13, 3,227 milliamp hours, 12.4 watt hours. Specialized processing is ubiquitous in mobile systems. Apple A15 Bionic in iPhone 13 and 14. $15 billion transistors, 6-core GPU. Two big CPU cores for small efficiency cores. Apple's designed multi-core GPU neural engine for DNN acceleration, image, video encode, decode processor, motion sensor processor. Specialized processing is ubiquitous in mobile systems. Basically, they're bringing all these like specialized things into hardware to make them more efficient, and draw less power and just generally perform better. There's probably like video encoding stuff here. Yeah, here it is. Image, video, encode, decode processor. Okay, now we're back here. Parallel plus specialized hardware achieving high efficiency will be a key theme in this class. We will discuss how modern systems not only use many processing units, but also utilize specialized processing units to achieve high levels of power efficiency.
Again, we're going to talk to be parallel. You got to be efficient. And one thing we're going to talk about in multiple lectures this year is how the architects of the world are saying we are not going to, if we have to be more efficient, we cannot provide you general purpose cores.
Yeah.
We're going to have to provide you much more specialized cores that do specific tasks. So here, again, this is that iPhone, and now I'm highlighting some of the stuff down here. On this processor, there are 6 CPUs, 2 of which are big CPU cores that are really good, or are supposedly good at running single threads. There are 4 small CPU cores that are lower power and good for background stuff. And then there's a whole bunch of stuff on there for camera, neural networks, sensing, your heart monitor, all of this other stuff that's never even run on the CPU. It's run on specialized processing. That's true in the small. It's also true in the large, with Google building TPUs and Facebook announcing that they're building their own neural architectures, as well as in the valley these days, the large building special purpose processing infrastructure. The valley these days, the large number of companies that are building special purpose processing infrastructure just for machine.
It's interesting diffing these slides because I can see how things have changed just over 2 years. So you got TPU 3, Graph Core IPU. I'm actually not familiar with them. Apple Neural Engine, obviously familiar with that. You have Ampere GPU with tensor cores. I don't think that's state of the art. Let's see. Okay, so is Ampere just their branding around data center GPUs? Oh no, it is actually. Yeah. Yeah, it's in 2020. I don't think it's state of the art. What came after? Like, I'm on Blackwell now. NVIDIA Hopper was before that. There's like Feynman, Ampere, Blackwell, Feynman. I want to see a list of all of them. List of all NVIDIA architectures. I don't give a fuck about that. Okay, here we go. Microarchitectures. Fahrenheit, Celsius, Kelvin, all temperature related. Tesla, I remember that one. Wait a minute, these are when they lived, not, yeah, 2006. I could have sworn there was like 2013, there was like a Tesla. But maybe I'm wrong. Fermi, Kepler, Maxwell. I remember Tesla being in like 2013. Pascal, Volta, Turing, Ampere, Hopper, that was the big one for AI. Lovelace, Blackwell is the one that I'm on now. Rubin, Bear Rubin, and then Feynman's gonna be 2028. Feynman better blow the socks off of everyone else, because I feel like if you're gonna do Feynman, you gotta do it right. All right. The eponym is in this case is the person after whom the architecture is named. Listed are the person, their portrait, profession or area of expertise, their birth year, their death year, their country of origin, the microarchitecture named after them, and the year of the release of the GPU architecture. I just want a list of all of them. Is this dated? It doesn't have Feynman in it. Doesn't seem like it's dated. Just want a table. I want a table with all of them. Maybe if I just say all, list of all NVIDIA microarchitectures, and just not give it any names here. There we go. Category. There we go. Maybe it was Kepler. I could have sworn it was Tesla. But there's some graphics card. I was in Colorado, so it would have been Pascal. This is like the big game changer. I remember when this came out, Pascal. Oh, and then Turing was the one after it that everyone was anticipating. Maybe that's why I got confused with Tesla. Why is Feynman here, but not in the table? Oh, because it's only for the professional stuff. Whereas Blackwell was consumer and professional. I guess they're just like saying, fuck it, we're not building consumer stuff. Ada Lovelace. Hopper was the big the H100s. Ampere. That was in consumer. Volta, Pascal. Pascal made it into the Volta. Maybe this is why I was confused, because Tesla V 2017, but then Tesla 2006. Okay. That's enough looking at that. Let's go back to the slide here. So he now has AWS Trainium, which is going to be a project in this. Trainium did not exist, I guess, at the time here. Then Cerebrus Wafer Scale Engine. I've heard of them before. Yeah, like I said, Ampere is a little dated at this point. Samba Nova. So they kicked off the Intel Deep Learning Inference Accelerator and replaced it with AWS Trainium. Interesting choice there. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, kicked Intel off the slide there.
Shares about all of this throughout the course. Okay. All right, so I'll close up on the thing that I think is perhaps the most important. As you saw when you're walking around the classroom, moving data to the right place is going to be the most important thing we talk about in the class. When you think about parallelism, you're going to be thinking about what do I do at the same time and how do I get the data there. Okay? And here's some examples. So this is where I need to bring up memory, a term that I've used without defining so far in this lecture. So I've asked you what is a program. I've asked you what is an instruction and what does a processor do. And at some point we've said things like a processor issues instructions that modify state. And I said one of the aspects of that state could be values in memory. What did I mean by memory? Like, what is memory if you're a programmer?
RAM. Or
RAM
caches.
is an implementation of memory. Like, when I look at my x86 code, when I say store this value in memory, I'm not saying it's stored in DDR4. I'm not saying it's stored in on-chip HBM. What am I actually saying? Yeah.
It's like a scratch pad where you just specify the address, and it's a byte.
At the end of the day, all memory is, logically, abstractly, is an array of values. If you give me an address, memory will provide you the value stored at that address.
Program's memory address space. The computer's memory is organized in an array of bytes. Each byte is identified as its address and memory. Its position in an array will assume memory is byte addressable. The byte stored at address 8 has value 32. Byte stored at address 10, 16 has a value 128. In the illustration to the right, the program's memory address space is 32 bytes in size, so valid addresses range from 0 to 1F. 16 and 50? Oh, because you got 0 there.
how memory is implemented. In fact, we will. But I have not told you how it's implemented. So here's an example of that abstraction. I have a table of addresses. In this case, they're referring to the address as the address of a byte. And for every address, there's a value in memory. In this case, I've given you some values that are bytes between 0 and 255. Okay? So memory provides the abstractions that the byte stored at this address has this value. And a load and store to memory, let's say if we're just talking about byte size loads and stores, it says the address at this, the value at this address needs to be set to this value. That's all memory ever is. So a processor has two places where it can store values. It can store values in its registers, and it can store values in memory. And there's example of an instruction might be move the value from memory into a processor register. So I say, go ahead, hey processor, take the value stored at this address, which happens to be 42, and move it to a register, for example, register R0. And what's the effect of that operation? How will my state change? How will the state of this program change if we execute this instruction?
Register up there.
R0.
Yeah.
R0 will have what value?
42.
We'll have 42. It says go ask memory for the value at 42, and you get it exactly. So I didn't show the update. Okay, so you should think about a processor asks memory for information and memory provides it. Now for implementation reasons, memory might take a while. And so, for example, if a processor asks for the data, it may come some point in the future, right? So in this diagram, memory had a very long latency, 2 seconds. But the latency of memory, if it was stored in DRAM, which is a very common implementation of memory, can be hundreds of processor cycles. So imagine if you had a sequence like this: load from memory this address into this register, load from memory this address into this register, then add those two values.
Processor stall can't make progress when it cannot run the next instruction in an instruction stream because future instructions depend on a previous instruction that is not yet complete. Actually, memory is a major source of stalls. So LD load register 0, load memory R2, load the address, load the byte at address stored in R2 into R0. And same thing with R3 into R1. Once those are loaded, then we can do an add on to R0 and R1 and store it into R0. Can't execute add instruction until data from memory R2 and R3 have been loaded from memory. Memory X time, there's hundreds of cycles. Memory X time is a measure of latency.
Cycles to actually get that data. Okay. So what can we do about that? A processor has a detail in it. So I have a processor with execution, registers, fetch and decode, and memory's off over here. What is a cache? What is a cache? You know, not this, but
A small amount of memory you can access frequently.
so if DRAM is storage for memory, a DRAM holds a lot of data, but is a storage mechanism that has high latency. A cache is another storage mechanism that can't hold that much data, but has very low latency. So if DRAM is my garage, cache is my desktop in my office, right? Less space, but much faster to access. So now we're talking about implementation of memory. A processor not only has stuff to execute instructions, it has a little bit of storage in it, a little bit of storage that's used to keep values in memory, a copy of those values to make it easier to access. Okay? So in this example, I might have a memory address space that in this case is 16 bytes, and I have a data cache that can hold 2 bytes. See that? So there's a little bit of a question of what data goes in this cache, and we're not going to even talk about it in this class very much. But I want you to just think about it as the cache is going to function of whenever it needs to put something going to kick the last thing out. Okay? So if you give me 1 minute or 2 minutes, I should be able to finish up on time. So imagine that this is memory. These are, look, memory. I'm not telling you how it's implemented. It's just an array of 16 bytes. Now, I want you to imagine that a processor issues instructions to access these addresses. So there's an instruction to access 0, 1, 2, 3, 2, back to 1, 4, 1, and so on and so on. So the program's order is kind of going down this way. Okay? So when the program accesses the value, I need the value at 0, address 0, it's going to need to load some data from memory. Now here's one implementation detail that we can't get around. Caches transfer data is transferred from out in memory onto on-chip caches in the granularity of some number of bytes. That typically is called the cache line. So in this illustration, let's just say that that cache line is 4 bytes, and I have a cache with room for 2 cache lines. Okay? So when my program accesses address 0, it will bring an entire cache line, all the data for that pink box, into cache. So what happens when my program accesses address 1? The data's already there. And 3, the data's already there. And so on and so on, right? So these cache lines, these caches provide an interesting benefit. They assume that if you've accessed some data, you're going to access the data right next to it. So there's some value in reading through memory completely in the same order. Now what happens if I go back and want to access 2 again? It's already there. So they also have a benefit of when I access things over and over, it's really quick. What happens if I hit 1? Again, it's there. 1, again, it's there, and so on and so on. So I'll finish this sequence up tomorrow, but I want to end with one fun thing. Effective caches. fun thing. This is the effect of caches. So if the data is stored out in DRAM memory, you're going to have to wait for a while. If it's stored in certain processor caches, you don't have to wait long at all. So I've made this to scale. If data is in cache, and the closest cache to the processor might hold a few kilobytes, that's how long it takes to access. A nearby cache, a little bit farther cache, a little bit longer. If data is not in cache, this is relatively how long it takes a load instruction to work. Okay, I'll end there. I'll let Ron get started, and we'll get into some details of why this is the case and the implications next time.
What is PJ? I'm not familiar with that unit. Picojoules? Yeah, it's probably picojoules. Because we're talking about energy cost. Always seek to reduce the amount of data movement in a computer. So, integer operation, 1 picojoule. Floating point operation is about 20 picojoules, reading 64 bits. From small local SRAM is about the same as a floating point operation. From a low power mobile DRAM, LPDDR. That's the stuff that's on the new framework laptop, LPDDR. Is about 1,200 picojoules. So it'd be 1.2 nanojoules. Reading 10 gigabytes per second from memory is about 1.6 watts. Entire power budget for mobile GPU is about 1 watt. Remember, phone is also running CPU, displays, radios, etc. iPhone 6 battery is about 7 watt hours. Exploiting locality matters. Bill Daly and Tom Olson. Okay, let's check them out. Bill Daly, NVIDIA, Tom Olson, ARM. I think this is yeah, this is when he gave it at Carnegie Mellon. Then he moved to Stanford. Lecture 21. I kind of like this yeah. Kind of like this course more than the Stanford one. Oh. That's weird, because these are Kayvon styled slides and similar sources. This is the CSAPP guy at Carnegie Mellon. I guess Kayvon was a TA for Randy Bryant then, probably, because he did the slides here. Yeah, these slides are very similar. I'm curious if they're still giving this course. because this was 2019. So this would be CMU that? Yeah. Very familiar website. 2026. If you look at projects, are they very similar? There's parallel computer architecture and programming. LZ compression. Oh, they went and really fleshed this out with projects. Designed by Claude. So these are actual projects. That's cool. Assignments. Parallel VLSI wire routing via OpenMP, MPI, writing assignments. Seems like they're just taking the same assignments from the what Kayvon left behind. Oh, these are hosted on YouTube, but they're private. Okay. They all private? Yeah. They don't mention using it in projects, so interesting. These are some pretty impressive projects. These guys are legit. Some of these I'd actually benefit from reading. like this one on GPGPU. Anyways, I was searching for this reference here, and it came up with Carnegie. Oh no, sorry. Just so bizarre seeing Kayvon's kind of style of his slides and. Yeah, that's what the vibe I'm getting. Demanding and hardcore. Oh. Electrical and computer engineering, probably. Yeah, electrical and computer engineering. Okay, well, it's interesting that CMU has a very similar course to this one. Kayvon seems to be the originator of most of the material. Yeah, so I really would prefer to just do his course, but the other one, just looking through some of the lectures, it seems like they've also developed the material really well in their own direction and gotten a little bit deeper into the weeds. Yeah. Okay. This is the first version of it. Probably missing a style sheet, that's why it's messed up. Okay, I still wanted to find this freaking reference, but I'm gonna move on from there. Okay. Summary: single thread of control performance is improving very slowly. To run programs significantly faster, programs must utilize multiple processor elements or specialized processor hardware, which means you need to know how to reason about and write parallel and efficient code. Writing parallel programs can be challenging, requires problem partitioning, communication synchronization. Knowledge of machine characteristics is important, in particular understand data movement. I suspect you will find that modern computers have tremendously more parsing power than you might realize if you just use it efficiently. Okay, cool. Let's go on to the next lecture, I guess. Jump to Stanford. Open. Yeah. 2, which would be parallel 2. Yeah.
So let's get going from a review from last time, because sometimes it's good to page back in what we learned. Okay, so I asked you a couple of trivial questions. One of those questions was, what is a computer program? And really, I meant, what is a computer program as we're going to think about it in this class from the perspective of a computer? So what was a computer program? Let's get in the habit of just shouting out things that are, maybe even obvious, and it'll just keep the... So a list of instructions, or if you want to even, I could ask you what's an instruction. If we want to be more abstract, it's just it's a list of commands. A program is a list of commands telling the machine you will do this, you will do that, right?
Okay, a modern multi-core processor, part 1, parallel computing, Kayvon's podium, Team Conrad, everyone is insufferable and I just want to study for CS 149, Team Gere, because these are students in the class. I would be in this group.
The slide is a list of processor instructions. At the end of the day, this program text turns into a list of commands. Okay. All right? And what did a processor do? Given a list of commands, what does a processor do? It executes those commands. I'll give you that one. But when we talk about executing the commands, what are the effects of those commands? What do they do? Modify state. And we talked about 2 types of state, right? We talked about registers, and we talked about main memory, right? So this processor, it executes instructions. I gave you this really simplistic notion, just enough detail to help us think about it. It's useful to think about, there's components of the processor that are about control. Given the program, what do I do next? Like, what's the next operation? Or if there's like a branch, where do I go next? I typically just have that as my orange boxes here, fetch and decode. Then you have a part of a processor, some of the hardware that's actually responsible for doing stuff. So I'm calling that the execution unit. And we have 2 forms of context. We have the register state of the processor, and then not shown on the diagram, we have memory. Right? And my simple processor last time was going to execute 1 instruction every clock tick, making progress. Right? But then we said something else. We said, well, if we look at the instructions in a program, if we look at those instructions, and this was a larger program, we can take a look at them and say, not all the instructions depend on the previous one in the sequence. So this was a sequence where I really recommend that you go offline and confirm to yourself that if these are the numbers of the instructions, and I'm representing those instructions as a node in the graph, there are certain dependencies. I have to do instruction 2, for example, after I do instructions 0 and 1. Because I can't add 2 numbers if I haven't brought them in from memory or something like that. And so we said that, in the same way that you can look at this program and go, I know I'm supposed to get an answer that's the same as if I ran these all serially. But if I had extra resources sitting around, I can do some of these things in parallel without really telling anybody that I changed the order, and they'll never know. All they'll see is that this program goes a little bit faster. And so we talked about this one idea last time of superscalar execution. And if you break down the word, it's kind of a weird word term, but if you think about it, it's like scalar execution, which is like doing one thing at a time. And then the superscalar is kind of like a fancy, technical term for saying we're actually doing a little bit more than that, but your program is still saying I'm doing one thing at a time. Right? So it's something that's going on under the hood. So this was the first thing that we talked about where there was a little bit difference between the abstraction, the meaning of a program, A program is a list of instructions and says if you perform these operations on this state, at the end of the day, you should get this answer. Then there's the implementation in a modern processor that says, we can do them in a little bit different order. It'll be better for you, and you'll never know. Okay. So that was a little bit what we talked about with processing. We also talked a little bit about memory, and I asked you what was memory. So in the same way, if I ask you what is a program, it's just a list of commands where those commands modify state in a machine. What is memory? Yeah, memory is just, logically, abstractly, it's just an array of bytes. It's part of that state for that program. And if a program says, please read the value at address 42, memory says, well, address 42 has some value, and sure, I'll give you that value. Right? If a processor says, write the value to address, write the value foobar to address 42, well, memory says, okay, I'll take in that value, and I'll put the value foobar there. Okay? So we talked about memory just being a big array of bytes. But we didn't talk very much about, and I even showed you, but we didn't talk very much about implementation. So notice how I'm setting this up over and over. There's what something means, it's semantics, like add these two numbers, then add those two numbers. Or there is an array of addresses, and every address has a value. And then the underlying implementation of that. Okay? So if I tell you memory, many of you might say the word DRAM, or remember a big stick of memory that you might have shoved into a laptop at some time, or something like that, right? And so what a DRAM chip does is it provides, it's the implementation of this abstraction. You send that DRAM chip a command that says, give me the value that's stored at address, hex.
Sorry, I got distracted there. I need to rewind.
Doing one thing at a time. Right? So it's something that's going on under the hood. So this was the first thing that we talked about where there was a little bit difference between the abstraction, the meaning of a program. A program is a list of instructions and says if you perform these operations on this state, at the end of the day, you should get this answer. Then there's the implementation in a modern processor that says, we can do them in a little bit different order. It'll be better for you, and you'll never know. Okay. So that was a little bit what we talked about with processing. We also talked a little bit about memory, and I asked you what was memory. So in the same way, if I ask you what is a program, it's just a list of commands where those commands modify state in a machine. What is memory? Yeah, memory is just, logically, abstractly, it's just an array of bytes. It's part of that state for that program. And if a program says, please read the value at address 42, memory says, well, address 42 has some value, and sure, I'll give you that value. Right? If a processor says, write the value to address, write the value foobar to address 42, well, memory says, okay, I'll take in that value, and I'll put the value foobar there. Okay? So we talked about memory just being a big array of bytes. But we didn't talk very much about, and I even showed you, but we didn't talk very much about implementation. So notice how I'm setting this up over and over. There's what something means, it's semantics, like add these two numbers, then add those two numbers. Or there is an array of addresses, and every address has a value. And then the underlying implementation.
Okay, you had a few more slides here that I'll go over. So, pretty basic shit here. I think we already looked at these slides before. Now he's talking about caches. Okay.
That. Okay. So if I tell you memory, many of you might say the word DRAM, or remember a big stick of memory that you might have shoved into a laptop at some time, or something like that, right? And so what a DRAM chip does is it provides, it's the implementation of this abstraction. You send that DRAM chip a command that says, give me the value that's stored at address, hex B, and this memory chip will send 255 back. But we talked about last time how it could take a while to go get that message out there to memory and come back. And so all modern systems have some form of a cache. And this cache is another form of storage that's part of the implementation of memory. But if the processor says, I need address 4, well, that value might be stored in cache, and it can get the answer much, much faster. So that was kind of right where we left off last time. Any questions? Just trying to, I often overlap just a little bit because it's good. Yes, sir. Oh. Dynamic RAM? Yeah, just dynamic RAM. And it's dynamic in that if you cut the power, as opposed to something that's persistent, like SSD or embedded. Okay.
So SRAM is static, but if you cut the power, it also loses its values. It's dynamic in that it has to be refreshed, whereas static does not need to be refreshed.
Even reading a value destroys the value. So when you read a value, you actually got to put it back, otherwise you lose it. But, for fun, we actually have a 30 minutes on DRAM, very, very much at the end of class. But for now, you should think about it as it's far away. And since it's far away, it's like it's standing in the back of the room, or it's storage in your garage or something like that. If you want to go get something there, it's going to take a little bit. And you should think about the cache as like what's right on my desk.
So these addresses that you've listed out, they're existing on the VM, right?
Don't think about implementation. They're just addresses. I have something, I have this concept. I have memory. Memory takes a value, an address, it gives you a value. DRAM is one way to implement that. The cache is giving another way to implement that. And this is something we haven't stressed very much in the class in previous years, and so this is kind of, we're trying to, don't think of.
So these addresses that you've listed out, they're existing on the VM, right?
Don't think about implementation. One is even details of how a data cache works that are kind of useful to think about. One is, even though memory says if you give me an address, I'll give you a value, the underlying implementation in any modern system that I know about will move data from memory into the cache at some larger granularity of cache lines. So in this figure, this cache holds data for 2 cache lines. Each of those cache lines is 4 bytes. So the bytes store, beginning at address 4, so 4, 5, 6, 7, these are the values out in memory that are replicated in the cache. You should be able to confirm that if I did not mess up my figure, right, 0060. Okay? So this is a cache that has the ability to replicate 8 bytes. It's organized into 2 cache lines of 4 bytes each. And what I'm highlighting in red is sort of the place in the address space that corresponds to these 2 cache lines. I've seen a bunch of questions, yeah.
Address you want to set. And if it's 0x5, will we just fetch the next 4 addresses of 0x5?
Yeah, good question. Think about you're going to access and move data from DRAM memory onto the chip in the granularity of 4 bytes rooted at address mod 4. So if you want address 5, the actual command out to memory is give me the cache line of 4.
Do different execution units have different caches, or is there a...
Not going to answer the question just yet. I just want everybody to learn it for one processor just yet. Absolutely, yes, but and you probably already thinking about how the heck if I replicate data all over the place, how do I keep things consistent? You are correct, but not today. Yeah.
Keep DRAM so far away.
Why not put a garage on my desk? Cool. Yeah.
Sorry, maybe you could explain one more time exactly what a cache line definitionally.
Yeah, sure. So what is memory? Memory is an address space and a value at every address. Somehow we have to implement that. So somewhere in the system, I need to have storage for every address. And typically, that is your off-chip memory these days. Okay. Now, a cache is just keeping a copy of this information right on my desktop. Okay. Now, the organization of almost any modern cache, anything you get on any chip that you're probably going to run, is that data is going to move between memory and the cache at the granularity of lines. So on an Intel chip, that's a 64-byte cache line. On my diagram, it's a 4-byte cache line, because I didn't want to draw 64 numbers. Okay. And so if you want address 5 in my cache, you're going to go ask memory, give me all the information for the line starting at address 4. Does that make sense? Okay. And next slide, I'm going to get into why we work at granularity too. Yeah. Okay.
From which you note, like, take things is basically always multiples of 4 or multiples of cache lines.
Multiples of cache. So we're going to work at that because we don't want to have a dynamic allocation situation here. This is going to be hardware. The whole point is to be able to access. This processor says I want address 5. And we say load address 5. Okay, let's think about this. What happens if the processor says I want to load address? Actually, I'm going to go with something else. Address 5. Conceptually, it's asking memory, please give me the value at address 5. But what's first going to do is it's going to ask the cache, hey, do you have address 5? And the cache is going to go, yeah, I do actually. It has value 0. Right? If the cache doesn't have the value, now we have to go get it. And the cache is going to ask memory, hey, can I get the line that contains 5? And that's when those 4 values come in this case. So let's think about it in a slightly richer situation. This is what we were going through right at the end of class. In the class, nobody knows, everybody's tired, nobody remembers anything anyway, so we're doing it again. Okay? So here is the value of memory. Notice that I'm really saying memory, and I'm not saying DRAM or any implementation, even though almost all of us, if we say memory in computer architecture, we're probably thinking about off-chip stuff. Okay? So this is just the state. This is the state of my program, these values. And here is a list of addresses that my program's going to access. So it's going to be like, I'm going to access address 0, then address 1, then address 2 in time. Okay? And what I'm going to show here is what is the cache doing in response to those processor actions. So let's say that the program says, please load the value at address 0. And let's just start from the place where there's nothing in the cache, or everything's in the value cache. Well, the cache is going to go, wait a minute, I don't have that value. So it's going to go ask memory for a cache line. Or DRAM, right, so these are my cache lines. Sorry, I didn't draw it. Right? So when we say, hey, I need address 0, the cache goes, you never asked me for that before, why would I have it? This term, so it's a cache miss. The value is not in the cache. And if you read a computer architecture textbook, they taxonomize the reason for these misses. And so in this case, I wrote on the slide cold miss because we have never even touched that data before. There's really no reason it should be in the cache. So the idea is that the data is cold compared to data that's hot that you're often accessing. So notice what happened in the cache state. The cache now has one valid line in it, and it's the line beginning at address 0. So that may have taken a while. There might be some real latency in that operation. Now what happens when the processor says in some later instruction, sometime later in the program, the cache hasn't changed, nothing's changed, it's done no other memory, and it says, you know what, I want to read address 1. What does the cache say? It's like, I got address 1, that's a hit, nothing happens, right? So that could potentially be really, really fast. And the same thing can happen for 2, 3, and what happens if I go back to 2? We're good, another hit, 1, another hit, 4. Don't have that, that's got to get brought in. And now my cache in this example has capacity for 2 lines, so we'll just put that other thing in. When I go back to 1, what happens? I'm good, exactly. So one thing I want you to take away from this slide is actually the cache is sort of solving 2 problems at the same time. I'm actually going to go to the second one first. The one that I kind of set this up for is if you've already touched data, if you've already accessed data, the cache has it, which means all subsequent accesses will be faster. So in general, one of the big reasons for a cache is that if I'm touching stuff a lot, the paper that I'm working on right now, the homework that I'm grading, that's why I keep it on my desk. I don't take it to the garage every single time I want to look at it. Okay? So that's this notion of temporal locality, back-to-back accesses in time. That data's sitting there. So that's what's helping you with, preventing me from going out and looking at it. The other thing that you might have noticed is that this granularity of operating at the granularity of lines, first of all, bulk transfers are almost always efficient. So I can transfer data efficiently to the cache. But it's based on the assumption that if I access address 0, oftentimes programs then go access 1, 2, and 3 too, because they're like running right down an array, for example. Okay? So there's actually 2 forms of the way reducing latency here. One form is almost like the line is functioning as a prefetch for the next items in the array. The second one is by bringing the data in now, I'm assuming you're probably going to touch it again. Like a common thing would be to read something, do some logic, and then update it. So there's already two memory accesses. Okay? Now I'm going to throw out one more pattern for you, which is kind of interesting. Same cache. And now what I'm going to do is I'm going to read right down an array. Notice that the address is just increasing by a byte every time. Except I am, yeah, okay. So let's just do it. So hit, right? Hit. Now what happens? Miss, good. Hit. But what do? My cache is full. So now we got to throw something out, right? And last time I told you that we're going to take, in this class, we're going to assume a very simple policy of least recently used. There's some questions on the website about this. So the line that I have touched least recently, the longest time ago, is the one that I'm least likely, that's the assumption, to touch again. And in this case, what color would it be? It's red. So we're going to drop red and bring in green. Okay, so this is a cold miss on green, right? Because I've never touched green before. It's the first time I touched this data. So this will continue. Hit. Then we get to address 12 or hex C. It's another cold miss, and we got to throw out blue. Exactly. This question somewhere? Yes.
In computer architecture, isn't this called capacity miss since you're throwing something out?
No, this is a cold miss. It's the first time you touch the data. The name of the miss is relative to the data that I'm accessing. If we would have had an infinitely sized cache, I still would have missed here, right? First time I touched it. But your question is relevant now. Your question is relevant now. So what happens when I go back? Yeah, well, so here, look what's happened. I have already accessed address 0 right at the very beginning. If I had an infinitely large cache, or arguably a cache that could store 16 bytes, that would have been a hit. So that's a miss that occurred because of actually I even got that wrong. That's capacity miss. Sorry. Hold on. 1 second. Yeah, my bad. Yeah. So this is a miss that occurred only because the cache has a finite size. If I could have put my garage on my desk, I would have been hitting on everything. You asked me about capacity miss. A capacity miss is actually a miss that we will not talk about in this class, but it comes from the fact that the cache might have been big enough, but the organization of where data goes doesn't allow the data to still be there. So we have to talk. Oh, sorry, yeah, sorry. A conflict miss is one where the organization of the cache means that, like, hey, I could put somewhere if I could put any data anywhere in the cache, but increasingly large caches tend to have policies that say this data can only go here and this data can only go here. Yeah.
the change in names? Is that anything different when it comes to this miss than the other misses? Like,
There's only no. I mean, the name is giving you a reason. And really, if you think about it as so, when you evict something, when you evict a line, your behavior will be different based on whether or not that line has been written to. Because if it hasn't been written to and only read, you just toss it. If it has been written to, you got to push that data back out to memory. So that's the biggest difference. So like 0, 1, 2, 3, 4.
Yeah, and then we do 0, 5, so 0, 0, 4. I wonder if you have an going on 2 line, go from 5 to.
No. Okay. So this would be a good thing for you to work out. But what I do want to say is this is similar to the earlier question. The mapping of cache lines to addresses. That is fixed. A cache doesn't even think about addresses really. It thinks about cache lines. And so I've just divided my address space up into these cache lines, mod cache line size. So if you decided to go, I want to read 0, 1, 2, 3, 5. 5 would trigger a load of the blue cache line. So what you've done is you've actually reduced the spatial locality of your accesses. So if you did 0, 1, 2, 3, 5, 6, 7, 8, 10, you just would be loading 4 values in this case, the cache line, and never touching one of them. Right? So you're incurring memory traffic or communication that you didn't need, but that's just the way the underlying implementation works. Okay, take 2 more questions and I'll keep it moving. Yeah.
I'm wondering if you could say a little bit more about the difference between capacity and capacity.
I'd rather not right now, actually. Because I don't believe that anybody has had any kind of sensitivity or that kind of stuff. So you're asking questions about how to design real caches now. And, yeah.
So maybe I'm a late thing, but when we talk about capacity mix and full mix, the processor doesn't know it was capacity mix.
Doesn't matter. Yeah, maybe in hindsight, maybe I should just miss. but for the sake of the class, it's a miss. Either way, I don't have the data. I've got to go get it, and I need to invoke my eviction policy to figure out who's leading. Yeah. The reason for that doesn't matter. The only thing that the reason matters for would be like, you might be able to, like, if you knew the reason, you might be able to change your program a little bit to avoid this. Okay, all good? All right, last one.
Sure. What's the overhead for like loading in the cache line? And if there's a significant overhead, is there like a ratio of like loads in the cache line is, and you need more for you like time?
We're going to slowly graduate towards all that because the reason why I'm spending all the time on a cache is for those kind of reasons. But the main thing that I want you to take away is that caches exist. They're an implementation detail. If I took the cache out of the computer, you would get the same results. It just may run slower. Right? That's the most important thing. And the caches exist to reduce the latency of memory access so that this processor is not waiting. Now, under the hood, if I had to elaborate a little bit more, in the same way that like I have a desktop, a filing cabinet, a hallway closet, and a garage, and I put different stuff in those different storages based on how often I might need them, most modern computers have a hierarchy of various caches. And I think a reasonable rule of thumb is that if a unit of storage is bigger, it is farther away, it has higher latency to access. And we'll also talk about how it actually has higher energy to access and stuff like that. But for example, if you rip open most modern machines, you usually see like a L1 cache that's pretty small, a few kilobytes, right next to the processor that can be accessed in a few cycles. If you miss the L1, you'll ask the L2. If you miss the L2, often you'll see an L3. And if you miss the L3, you'll go out to DRAM. And this is something I showed you to finish class up. You started to hint about what are the consequences of missing. So this graph is to scale of the number of cycles a few years ago now on Intel CPUs that it took. If you issued an instruction, how long would it take to get the data? And an L1 cache hit was about 4 cycles. Pipelines, you can actually really cover that. So, like if I did it in animation, not that fast. If you get it out of the next level of cache, it's going to take a little bit longer. The next level of cache is going to take a little bit longer. And if you miss this cache hierarchy, you're waiting. You're definitely waiting. So consider a system that's like load, do some math, load, do some math. We're worried about using 4 cores, getting a 4x speed up, and if you get your memory wrong, you could potentially be off by a factor of 250. Okay? So the scale of these effects that deal with data movement are enormous. Okay, so I want you to just, that's like us finishing up last time. Yeah.
You're taking it from RAM when you get it. Is that when you get it?
Well, that's the latency that I'm talking about. Like think about it this way: is if the data is in DRAM and the processor says I want address X, let's think about the moving it from DRAM into the L3, bringing it from the L3 to the L2, L2 to the L1, all the way to the processor. That's 250.
Is there no way to just bring it back in one?
There are ways. Yeah, there are ways. There are instructions you can say is read this data and I want you to bypass all the caches. I don't think they're as much about reducing the latency as they are about not loading your caches. I have a feeling like it actually probably goes through the whole path and then just doesn't get stored. Would be how I would implement it, I guess. Yeah. Okay. Oops. Shoot. All right, I'm going to re-emphasize this, but apparently Keynote won't let me go through it until the animation stuff. Yeah, while we're waiting, yes. Go ahead. Yeah, that was the question here. Is like, are there really any benefits on a modern system of bypassing the whole thing? They're not going to be latency benefits. They're not going to be latency benefits. Okay, so let's put memory aside. It's coming back at the end of the day. But now let's go back to processing a little bit. So the rest of the lecture is going to be talking about
I need to silence my phone. I'll be right back. Let's see. We got 30 minutes left on this. Is that how much? Why does it say negative 24? 24 plus 27 is less than an hour, and this is hour 16. Maybe because of speed? If I hit backspace, will that fix it? Yeah, okay. So going at 2x, I got that much time left. Alright, trying to calculate in my head how quickly I can get off here and get dinner. Okay. So he has a slide here about data movement. It has high energy cost. Rule of thumb in modern systems design always seek to reduce the amount of data. I think we already went over this in the last slide, so I'll just skip ahead here.
On parallelism, on how we start adding more and more capabilities about kind of, but so I wanna, let's put memory aside, it's coming back at the end of the day. But now let's go back to processing a little bit. So the rest of the lecture is gonna be talking about kind of 3 major ideas on parallelism, on how we start adding more and more capability to do more stuff into a machine. And we're gonna come full circle and end up saying some of these ideas are about combating this latency problem. So I already gave you caches as one way to combat the latency problem. Okay, and then so here's an example program that I'm going to use as a running example for the next 50 minutes, or the next 47 minutes. Okay? This is some straight line C code. Take a look at it, make sure you know what it does. What it does is it takes its input in array X, it reads values, n values from the array X, it writes n values to the array Y, and what it does is for every input value X, it computes the sign, or approximates the sign of X, given...
Okay, he's going a little bit faster than I thought. I can't really keep up with this, so let me key concepts about how modern parallel processors achieve high throughput. 2 concern parallel execution, multi-core and SIMD parallel execution. 1 addresses the challenges in memory latency, multi-threading. Understanding these basics will help you understand and optimize the performance of your parallel programs, gain intuition about what workloads might benefit from fast parallel machines. So then he goes in here, he has example program, it's the sign of X. And there's a n term here, int of terms, float x, float y. So compute sign of x using Taylor expansion. So terms, it's the terms in the Taylor series, how many terms you want to. So it'd be basically an accuracy count. If you increase terms, you'll get more accurate calculation of sign x for each element of an array of n floating point numbers. So you got your input array x and your output array y, and there's n elements in that array. You then iterate, so this is going to be a serial computation. This is one that, yeah, I can understand why you'd want to parallelize this, because none of these have any data dependency between each other. So vectorization would work here, but also just like parallel execution would work here. So we got for I is equal to 0, I is less than n, I plus plus, so we're ranging over every element. And we do a memory read into a register of the input. We then bring it to the third power to compute the numerator. And then our denominator is going to be 6, which is 3 factorial. And our sign is -1, which gives us a subtraction on that. So that would be the first value. And where do we assign into here? So the value basically is the output of each iteration. So this register value here is the important thing. And then we do our memory access at the end here to assign back into the new location. So we compute a numerator and denominator starting at the first term here, or second term, depending on your perspective. And then for j is equal to 1, j is less than or equal to terms, j plus plus. So we're considering this a term. No, we're considering this term because we start at 1 here. And it's less than or equal. Okay. So then we say, okay, value is going to be equal to, oh, so this is the first term. So J1 is this term here. We say multiply sign times the numerator divided by the denominator. That computes the value. And then we compute the next numerator by multiplying it by x squared, because we go from x cubed to x to the 5th to x to the 7th. We're going up 2. So you have to multiply that out. And then the denominator is going to be instead of 3 factorial, will be 5, 7, so we're going up by 2 each time. So we have to multiply by 4 and 5, which would be, in this case, j is 1. So 2 times 1 would be 2, plus 2 would be 4. Okay. Yeah. And then 5 would be plus 3. So this multiplication is redundant. Hopefully that can get pulled out by the compiler into a register, so you don't have to do 2 multiplications. I'd have to look at the assembly, but that's a potential optimization there, just storing that into a temporary register. And then we just toggle the sign by multiplying by -1, and then once we're done with all the terms, then we assign it to the value. Makes total sense.
Approximation using the Taylor expansion. N values to the array x. We look at it, make sure you 50 minutes. Okay, and then so here's an example program that I'm going to use as a running example for the next 50 minutes, or next 47 minutes. Okay, this is some straight line C code. Take a look at it, make sure you know what it does. What it does is it takes its input in array x, it reads values, n values from the array x, it writes n values to the array y, and what it does is for every input value x, it computes the sign, or approximates the sign of x, given a numerical approximation using the Taylor expansion. So like how it computes the sign of x doesn't matter. The only thing that matters really is you look at the C code, you go, okay, I've got a piece of C code for I equals, outermost loop for I equals 0 to n. For every input element, perform a computation that ultimately computes value and is stored to the output element. The inner for loop is just an iterative algorithm to approximate sign. Okay. So what this is doing doesn't really matter. You can just think about this as some function that takes its input x sub I and outputs sign of x sub I. Any questions about the code? Does anyone need any more time to? Okay, so that's all I want you to think about. And my illustration on the right just shows you all the input values of x and the output values of y. Okay, right, so it just does that. Okay, so if we compile this program, we run Clang or GCC, pick your favorite compiler, we're going to get out a sequence of instructions, right, for this program. And I want you to kind of focus on the sequence of instructions that's the basic block inside the for loop. So at the moment we're going to think about, there's a sequence of instructions that says, once I load x sub I, here's all the stuff I have to do to produce the value that is then stored to y sub I. And now given that sequence of instructions, we're going to execute it, right? Like, so that sequence of instructions, the processor is going to say, okay, what's the next one? Oh, it's a load of this value, then it's a multiply, and so on and so on. It'll run those instructions, it'll produce a value, and at some point at the end of that, there'll be a store instruction, which is store this value to the address given by x sub I. And just to repeat myself, if that processor is smart, it might look into that program, into that instruction sequence, and go, yeah, there's some of those instructions that can be done in parallel, right? Let me back up and let's look at it. Like, we certainly can find some stuff, right? Like this, computing the numerator is independent of computing the denominator, right? So there's a little bit of instruction level parallelism there. And so one way for me to run this program a little bit faster would be to take the superscalar idea. I'm going to build a processor. It still has like one set of registers. It has access to memory. But it has the ability to kind of figure out if there's 2 instructions that can be done in parallel, and it has 2 execution units to do that if it wants to. Again, like you compile your program in C, you see a sequence of instructions. Processor Intel does this or AMD does this under the hood. You never know, right? But in this program, or at least in this region of the program, at least, there's not any ILP. Just in those instructions that I chose, they are all dependent. So this processor, if it was running that sequence of instructions, is only going to be making use of one of these execution units and one of these fetch and decodes. Right? There's no ILP here. So this gets back to the broader thing. But there's tons of parallelism in this program, right? Because we can process every element of this array completely in parallel. But if all the processor is doing is kind of looking at like micro instruction sequences, all it sees is dependent instructions. It doesn't have the ability, or it would be intractable to have the ability to look over a huge window of the program, like that outer for loop, and go, oh, even though this is a for loop in C++, technically every loop iteration is dependent because there's I++. They all seem to be accessing different input variables. That's the type of analysis that goes well beyond what could happen in hardware. So what hardware architects did is they said, you know what, let's just assume that the programmer tells us where that parallelism is, so we don't have to work so hard for it. So this is, I made that diagram that I had on the last slide just a little bit fancier. I said, look, like you had.
Okay, pre-multi-core AIR processor, majority of chip transistors used to perform operations that help make a single instruction stream run fast. So big data cache, out of order control logic, fancy branch predictor, memory prefetcher. Yep. Fetch decode, execution unit, more transistors, larger cache, smarter out of order logic, smarter branch predictor, etc.
Outside of this class, there's all this other fun stuff that's in a processor to make an instruction stream go faster. A lot of it's about not accessing memory. Like you might put a big old data cache that has a ton of transistors, hold a bunch of data on cache. You might actually have logic that predicts what memory you're going to access in the future as a prefetcher. They had all this fancy stuff in there to try and make the inner loop go as fast as possible. But there's this outer loop that's trivial to parallelize. So idea number one is let's take some of this fancy stuff out. Maybe a little bit smaller data cache. We're not going to maybe do as much out-of-order execution or anything like that. And if we clear all that stuff out, we just have our basic processor with just a few, which use far fewer transistors. And I'm going to use all those transistors I have on a modern chip to just make more, just replicate this, to make more of these processors. So now I have a processor, but it's a parallel processor. And this is, I'm going to use the term core, but there's nothing precise about this in the industry. So now I have
Rather than use transistors to increase sophistication of processor logic that accelerates the single instruction stream, e.g. out-of-order speculative operations, use increasing transistor count to add more cores to a processor. Okay. Simpler cores, each core may be slower at running a single instruction stream than our original fancy core, but there are now 2 cores, potential for speed up. So this should be thread level parallelism.
everything that was needed to run one instruction stream. So if I give this processor 2 instruction streams and say, hey, core 0, run this instruction stream, and core 2, do that instruction stream, I might be better off, right? Like, for example, maybe these cores, because they don't have all the fancy stuff in them, can run one instruction stream 25% slower. Right? Maybe they take more cache misses because the cache is smaller. Maybe they mispredicted a branch or something like that. But now, with those same resources, I can have 2 of these things. And if I put both of them running on different elements of the array at the same time, I have a 2-core processor that might run 1.5 times faster. Okay, see some questions. Yes? Yeah, we just duplicated everything. We duplicated the hardware for executing instructions. We duplicated the registers. There's an R0, R1, R2 here. There's an R0, R1, R2 here. And there's the ability for each of these processing cores to take a look at the instruction stream that they're supposed to run and say, my little executive here needs to run this instruction next. And if that instruction is multiply R0 and R0 and R1, that's modifying these registers.
I just think compared to what I used to, I could execute context. I'm not sure if that.
Yeah, we're duplicating everything. We're duplicating everything. Yeah.
So talking about the resources you just mentioned, so like so basically using two transistors, you have enough. You can actually create a superscalar processor or create like 2 cores.
2 simpler, yeah, exactly. Now notice that both my multi-core processor and a superscalar processor both have 2 fetch and decode units and 2 execution units, right? But I decided to organize them a little bit differently and now duplicate the execution context. So I got rid of all that logic to try and find ILP. I got rid of logic maybe to have a really big data cache to avoid stalls. But now I have the ability to, if you gave me 2 instruction streams, I'll guarantee that you'll run both of them and get double the performance. Yeah. It could, but then it's only working on stuff that it knows statically. In this case, modern advanced compilers probably could, but the minute I throw a small wrinkle in that program, the compiler's going to go, I don't know, I can't reason about this anymore, and we have to rely on the hardware. Yes.
Would you like to decide by just saying that instead, like I'm just doing chunks, taking a file and like, okay, so
Hold on, I love these comments because it's fun. You say, can't you trivially just do it? That's the point. In a program like this, which looks a lot like a tensor operation, right? It's trivial for you, the programmer, or maybe even a software compiler, to generate code that says, this is different from this, it's parallel, trust me. We don't need to rely on hardware to do it. So the observation is that doing that automatically in hardware is not an efficient use of resources. What's better is to push that up the stack. Okay? Now, right now, this is C code. This is valid compilable C code. If you compile it, client will kick out, unless you're turning on some very fancy stuff, a single instruction stream because the semantics of this program are serial. Okay? So if I take this program and I run it on my dual-core processor, I'm going to create one instruction stream to run on one of those cores, and those cores are wimpy cores. It's going to run slower. Does that make sense? Okay? So I've got to change my program. So let's do it in the only way that we know how, assuming that you've taken 111, is let's spawn some threads. So take a look at this program. Take a break, I've been talking a lot. Talk to your partner or your friend or your enemy or whatever for 45 seconds, and I want you to tell me what this program does, and specifically what I mean. It computes the same answer as everything I've shown you. But there's 2 threads. There's the original thread and there's the thread that I spawn. One thread deals with some elements, another thread deals with some other elements. What thread does what? Take 30 seconds to just talk that over.
Okay, so parallel sin x, we use our original sin x. Has the same signature. We have a thread with some args, and our n for the thing in the thread is going to be n divided by 2. And ours will also be n divided by 2, but there's a rounding issue, so they do n minus args n, which makes sense. Terms will still be terms. X will still be x, and the x and y will still be the same in the thread that responds. So it's working on the first section. Our main thread of execution is going to have to add onto x the number of elements it's handling. Makes sense. Then we spawn our thread, which just passes everything in args into sin x to do the work. We do others sin x in the main thread, and then we join. So we basically just wait for the other thread to complete. Pretty simple. Parallelization using 2 cores.
Tell me, how does this program divide the parallel work? Yeah.
So the main thread does the second half to which is sin x. The main program does the second half, and the thread does the first half.
Yeah. So I have 2 threads. They both call sin x. The main thread actually works on the pointers at x plus n, which is actually n over 2, are exact.
So this is C++ because it's using standard thread instead of pthread.
So the thread I spawned does the first half. The thread that I already had does the second half. Okay? That doesn't matter. What does matter is as the programmer, I've created 2 threads. And from the programmer's perspective, a thread. From the machine's perspective, 2 instruction streams. The operating system here, which we're not going to talk about, just says, oh, look, here's a program with 2 threads, 2 instruction streams. Hey, processor, here's 2 instruction streams. And the processor goes, OK, I'll run one on core 0 and the other one on core 1. Okay? But without me explicitly creating parallelism, or some magical compiler explicitly creating parallelism, this processor is not given 2 instruction streams to run. Now, another way to think about this is you're like, gosh, like this is kind of gnarly. I even had to ask you to parse the code. Really, the way you want to think about it is like, if I go back to the original program, you'd probably be like, it's a lot more intuitive just to like have some way to say that outer for loop is parallel or is independent. Like by saying, look, everything that's outer for loop, you can do independently on different threads if you want to. You go figure out what thread should do what. And so you should assume that in modern programming languages, whether it be PyTorch or any kind of programming language that has parallel constructs, there's almost always some way to have some form of a for loop, an iterator.
So this is data parallel expression and Kayvon's fictitious programming language with the for all construct. I think this is what the Intel compiler does, though, that we're going to use in this programming assignment. Declares that loop iterations are independent, even though I is used for all of these memory accesses. In this code, loop iterations are declared by the program to be independent. This information, you could imagine how a compiler might automatically generate threaded code for you.
Trust me, I know you can do all the loop iterations in parallel if you want to. Okay, so what I did here is I made up syntax. This is not valid C anymore. Imagine a for all loop where instead of saying I++, instead of empirically saying here's how we iterate, there's a for all loop. There's going to be n iterations. You can identify your current iteration by the variable I, and I guarantee you that I wrote the program. I know that all those iterations are potentially parallel. Like you can do them in parallel, and you'll get the same answer. We're good. Okay? And if I write code in this higher level of abstraction, shoot, like it's not hard at all. All of you could sit down and go, I know how I do that. I would actually, like if I was running on a machine with 2 cores, I would create 2 threads, and then I would create a for loop on each, and one of them would do half. You could kind of think through how you would transform this program into this program if you knew you were running on a 2-core processor. Right? Now imagine we weren't running on a 2-core processor, you were running on a 4-core processor. If you wrote code with pthreads like this, you would be like, shoot, I'm only actually going to use 2 of those 4 cores. Whereas that's why it's kind of useful to sort of think about how the programming model can give me a much more abstract way to just say, this stuff is independent, and however you want to schedule it in parallel, you can. Because if I start writing code like this, if I happen to run on a 4-core machine, under the hood, that runtime can spawn 4 threads. Or if I'm running on a 16-core machine, it can spawn 16 threads. I don't need to know as a programmer. All I'm doing is I'm saying, trust me, these iterations are independent. Create as many instruction streams as you feel appropriate on the computer that you're running on. Okay? So I can scale up to a lot of cores pretty quickly if I take out a lot of the fancy stuff. If I start like getting rid of a lot of superscalar execution, if I kind of maybe move to smaller caches, I do all the things that architects have done to make single instruction streams run fast. I can rip some of them out, and in a modern era, I can get a lot of cores on a chip. So here's an Intel CPU. If you look at a chip diagram, you can kind of see where the transistors for the various cores are. That's a 10-core Intel. This is actually the RTX 4090, and if you look closely, the replicated unit is about this size. There's about 144 of them on there. NVIDIA likes to call them SMs for shared multiprocessors, but that's the granularity of a duplication. Pull out your iPhone, and if you look at Apple's Bionic chip, there's 6 CPU cores in there. They're actually heterogeneous. They're not even the same design. So you have 2 cores that are bigger cores that have more of the big caches, the out-of-order execution in order to run single threads fast. And then for stuff where you have more parallelism, they have additional 4 small cores, where more of that superscalar stuff has been ripped out and things like that. Okay? All right. And yeah, we've kind of already discussed this a little bit. Okay, so I said that like if I write code in this kind of manner, I said here's what we need to compute, but here are the computations. There's another property of this code that's pretty nice. I'm saying that everything that is being done independently, it's actually doing the same thing. The body of the loop is being done, the same body of the loop is being done by all threads if I executed this thing. The only thing different is that they're loading and storing different values. Okay? So that gets me to the next major idea here. So what folks said is, in a lot of these modern applications, graphics for sure, any kind of numerical computing or data science, or anything like that, you're often working on code that looks a lot kind of like this. Like I've got a big array of values, I've got a tensor, I need to do the same thing on everything. So what they decided to do is now there's a change in my diagram, no change at all to the orange box. There's still a processor that grabs one operation per clock, can kind of like do the control, like, okay, what was it? Oh, it's an add, oh, it's a multiply, oh, it's a load. But now I've actually replicated my ALUs. So I have 8 ALUs on this diagram, or 8 execution units. And what's going to happen is like if the next instruction is an add, we're not just going to do one add on one value. We're going to do 8 adds on 8 different values. So all of these are kind of locked together with the same control. And for now, one way to think about it is I also took all the registers, R0, R1, or whatever, and I turned them into 8 wide vector registers. So when I say add, so let's see here. So I used to have a program that when we compile it, we would compile it to instructions that work on scalar registers, like 32-bit values or 64-bit values. That's what the C code does. But now I have a problem.
Intrinsic, AVX intrinsics. Looks like it's still in C. Functions available for C programmers. Intrinsic functions operate on vectors of 8 32-bit values. I wonder if I can get more than that with AVX 512. This is with AVX 256. So you can probably get 16 different 32-bit values on AVX 512.
Ability to run an instruction that runs on a vector of 8 values and should read and write vectors of registers.
I really want to understand these instructions, so we're iterating by 8 on this, which makes sense. The fact3 pre-computed constant here. I guess we need it to have an address. It needs to be addressable, which is why we didn't make it a constant. We signed it into a local variable here. That could be static as well. I don't see why that couldn't be static. It's not being mutated. But anyways, we go in here and we say load. So it's probably AVX 256. MM is for multimedia, I believe. But then what is this M over here for? You know, XMM, YMM, ZMM, that sort of thing. Load, PS, I don't know what PS is. But it's a function that you call, these intrinsics, and you call it on the memory reference of the array, sub I. So you can do pointer arithmetic here to simplify things instead of taking an address, but the compiler will figure that out for you. So maybe that's a more, like a better way of expressing it. But I like doing x plus I here to indicate that you're just taking x and you're advancing it by I elements. And you're just doing math on a pointer versus saying x sub I like this, which is a dereference. And then you get a reference to the dereference to cancel it out. It's a bit weird. Okay, and then we have M256 as the register type. I mean, technically it's like a local variable. It's not a register, but it will be a register at the end of the day. And then we store that into the value, the original value. Orig X. We then do a multiplication of it to raise it to the third power. We compute the denominator by just broadcasting the 3 factorial into all the elements of that, and we use SS for that, for the denominator. So there's going to be 8 different copies of it. This PS is probably like a width. So it's like the left is the width of the register, and the right is the width of the operation. Like what data you're operating on it within the register. I think that's what it is. So it's probably a scalar or something like that. I don't know. And then we do our division of the numerator and the denominator, and we multiply the numerator times the sign. Get this temp value, and then we then add that to value. I wonder if you even need temp here. I wonder why you need it. Seems like you could just chain this temp directly in here. This value is M256, yeah. Maybe you did that just to make the slides a little bit more readable. And then we compute our new numerator and denominator. And then we just multiply sign by -1. So sign is just an int. we don't use XMM to store that, but we do convert it here, interestingly, and then we do our store. Okay, I don't think I could write this myself from memory until I fully understand the pattern of the intrinsics. Also, like, you kind of have to pound define this stuff so that it works for, you have to make it generic, because some architectures are going to be 512, some are going to be 256, some are going to be lower than that. So like, you gotta basically figure out at runtime really which architecture you're on, and then dispatch to specific code for that architecture. And that complicates this a bit as well, doing all that stuff. So yeah,
generate these new instructions that I need is I can open up my favorite parallel programming library, and I can change every variable in my program to the equivalent variables using these macros, these intrinsic macros, that every variable here is a 256-bit or an 8 by 32-bit float vector. Okay, so all I did is I rewrote the program where I took here an int or a float, and I turned it into a float vector of 8 things, or an int vector of 8 things. And then notice that my for loop, my outermost for loop, is not for I equals 0 to n, but it's I equals 0 to n by 8. So every time through this for loop, I'm actually doing the same logic, but I'm doing it for 8 things. Okay? And I've also made the code almost impossible to read. Right? Okay. Yeah, so this is so now when this program gets compiled by a compiler that supports these little macro functions, the output are instructions that modify vectors, not instructions that modify scalars. So you see the difference. I changed my R0s to these XMMs just to indicate that there's something different. Okay? So my compiled program processes 8 elements simultaneously using vector instructions with one instruction stream. So I have one instruction stream, but the instructions now are these wide ones. Now I can combine that with multiple instruction streams. So if I take this new type of core and I apply it to my 16-core processor, I have a 16-core processor that runs 16 instruction streams, but the instructions in those streams are processing 8 pieces of data at once. So altogether, my chip has 16 cores, 16 instruction streams, 16 times 8, or 128 execution units, which means I can do work on 128 pieces of data at once. So arguably, I can maybe be going 128 times faster on the 16-core chip. Notice that you could imagine, if I asked you to, if you knew this was a for all loop, you could turn this for all loop, if you were a little compiler, in fact, assignment 1, you'll do this, into 16 threads and those vector instructions inside those threads, and change that for all loop for I equals 0 to n to for I equals 0 to n by 16, by 8. So you can imagine how, if I asked you to do this in one assignment, the value comes from you being told what is potentially independent. The value is not from the mechanical transformation into vector instructions or threads. Question, yeah?
If you were kind of like just taking your green light to show all the kinds of registers, is it just trivial and patch all that?
Well, we're going to have some, we've got to move that data.
Yes.
We are suspending disbelief temporarily on how costly it is to move data, and we're first getting set up on how to crank on that data. And then we're going to come back with the question at the end of, can we get the data there? Okay. So this is kind of like a pretty big intellectual change. I'd like everybody to there's a good time to raise your hand if you can't.
The program uses a for all declares the compiler the loop iterations are independent, and the same loop body will be executed on a large number of data elements. This abstraction can facilitate automatic generation of both multi-core, parallel core code, and vector instructions to make use of SIMD processing capabilities within a core.
Going on here, right? I have 16 threads running on a 16-core chip, and those threads, the instruction stream, contains instructions that are processing 8 wide vectors. And if I think of what's going on at any moment in time, there's 128 pieces of work getting done at any point in time. So if I perfectly parallelize and I compare my performance to my original starting processor that had 1 core and 1 ALU per core, I might be up to 128 times faster. Well, the first answer to your question is, now I have 8 execution units that can do 8 things per core, instead of 1 execution unit that can do 1 thing. Your real question is, well, why don't we just make 8 times more cores, right? And so what's going on is we're amortizing a lot of the costs of controlling or processing an instruction stream over these 8 execution units. And like in my cartoon diagram, notice that there's still 1 fetch and decode unit. Like you still do, what's the next instruction? Okay, that instruction, great. Now you're just going to say, I'm going to run that instruction on vector registers with my vector of ALUs. So this is a good idea, because I can amortize the costs of the processor across many execution units. And I can do that if my code does the same thing, needs the same logic for all of the elements.
In terms of resources involved, I think like a single, like 16 single core processor, like 16 core processors, I'm messing up the terminology, but basically 16 cores in that original.
You would be surprised, I know what you're getting at, how few resources are needed to produce an arithmetic unit compared to everything else, especially when it's not high-precision floating point. Yeah. So the idea here is those things are cheap. We can pack a chip full of those if the code is set up to use them. That's the main idea. And now we're going to get to something that might, oh, sorry, I have to go this way. Okay. Now there's this question, is the code set up to use them? So I'm going to change the example for just one slide. Imagine that this was my piece of code. For all n elements, do this logic. So for all n elements, every element can be processed independently. Do this logic, read the value, and then maybe you need to do the if statement, and maybe you need to do the else. But I just built a processor that has, every core has 8 execution units that have to do the same thing. And now I have iterations of the loop that some of them need these instructions and some of them need these instructions. So I'm going to diagram this out for you as going down the slide is like time as we execute the program. Going across the slide is what each of the ALUs are doing. This is just about what's going on in one core. So at the beginning of the program, the ALUs are they're doing what I just told you. Like they loaded x of I all in one big vector operation. They actually even can do the if t is greater, if for every iteration, if the value loaded is greater than 0. And they'll give a vector, a bool vector of trues and falses as a result of those tests. Notice that some of these iterations evaluate to true and some of them evaluate to false. What do you think happens next? Any ideas? Yeah. Because the rules of my underlying implementation are I execute 8 things at once, and they got to be the same instruction. And in this case, what I might do is I might say, you know what? I know that this code that I have to run has to run the instructions in the if branch, so let's do it. Let's run those instructions in the if branch, and then let's just mask off or not even run maybe like cancel out the operation of any ALU that's responsible for data that actually doesn't need that instruction. And then we're going to run the else branch, and we'll flip that mask. And so at the end of the day, not all ALUs are doing useful work. I built this chip that has 8 things in it because I know that if I could do 8 things at once, I got a lot of compute for free. But if code isn't set up to do 8 things at once, I'm essentially just spinning my wheels on some of those execution units that don't have anything to do. Can you see why the worst case is 1/8? Right. Question? Yeah.
Shouldn't it always do the true case and then?
So worst case is 1/8 peak performance because you might have just one thing going down true and everything else masked off.
First of all, 2 clarifications. Because if none of the iterations need the if case, we can be smarter about it and skip the thing. Yes. Yeah. So here's a question for you. Let's let me talk over. Can you give me the simplest piece of code that you can think of? And by simplest piece of code, I actually say, can you do it with one if statement? That overall, on average, this processor will be running at 1/8. Notice that it's not in this scenario because it's running at 3/8 efficiency up here and 5/8 efficiency down here. Can you give me a piece of code that will create a situation where we're at 1/8 efficiency? Give yourself some time to talk about it. And you only get to use one if statement. All right. Any thoughts?
Okay, so that'd be the next slide here, probably. Okay, can you think of a piece of code that yields the worst case performance on a processor with 8 wide SIMD execution? Hint, you can create it using only a single if. Well, it depends on the data, right? You can say if I is equal to some value mod n, then do this, and then you just handle the ith path, and then do it else, or you don't have to do the else. Basically, just be handling one element from the vector, but it's dependent on I in that situation.
Like take whatever's in the block, like put it into one equation and multiply by t greater than 0.0.
Okay, say that again. So we have this code here, and what goes in the yellow box?
Yeah, so we can just like multiply that by that Boolean statement above, plus that Boolean statement times whatever's in the else.
He wants you to actually instead of modify the condition, he wants you to modify the statements inside of the condition. I don't know if that's possible, right? Because like this is dependent on t. T is totally not known at compile time. It's determined at runtime. So if this whole thing is driven by the values in t that we don't have, right? Oh, but we do have the values in t, right? These are the values. If t is greater than 0, no, we don't have them because we'd be operating on. Oh, so that means that we know that these values are less than or equal to 0. Is that the assumption? So if you go back over here, so we want to exclude. So we can't change the condition, but we want to exclude 2 of these lanes. You can introduce another condition where you say if t is greater than 2, since we know the value 2 here. But if this is 8, then why is this thing not here? I don't know. I remember running into this last time with this lecture series. I didn't quite understand what he was getting at. You basically have to operate on only a single element. You could say if t is less than 2, which would give you only this vector that you're operating on. Let's see what he says.
Whereas in the yellow box was 0 times that thing. Okay. So you have the proper answer. And then in the other case, it'll be 0 times whatever's in the yellow box plus 1 times whatever's in the blue box. And then you'll get whatever's in the else. So you don't need those things.
You're trying. I see. Okay. So what you said was, I see what you're doing here. So I set up this thing with an if statement in the code, and what you're proposing is let's remove the if statement and the else statement altogether. The code is just the orange box followed by the blue box, and we get the same effect if we multiply these results by 0 at the appropriate time, and these results by 0 at the appropriate time. Okay. So that is a good implementation of this if statement. But what you've created is something that still does all the same instructions and has the same cost. So what you said is, like, if you want to compile this to a machine that has no if statements in the instructions, you actually given me a good lowering of the if statement to what's called predication. So good compiler optimization, but we're still running exactly the same performance as before. So what I'm looking for is a solution that, given that if statement, or given your implementation of that if statement, gets me running at 1/8 utilization. 100% utilization is every ALU is doing useful work on every step.
1/8 utilization. 1/8 at any given time or 1/8 at all times?
On almost all times. Yeah.
Should you modify it like if x of I is larger than x of I minus 1? Because then like the next branch has to depend on the previous one. So it's
like x of I mean, there's no dependency. Well, but we don't know the values of the data. So what data would you give me to make that?
So, yeah, I'm saying like you do the same kind of thing where you load like the block into a vector register, but if the output of each subsequent.
But you decide to put a sequential dependency between every iteration. Yes, you okay. By that definition, yes, you are running at worst case performance, but you made the entire program non-parallel. I'm actually thinking about something that stays with the parallel program. Yeah.
But you just say if I is odd.
If I is odd, then we're half and half, right?
Yeah, but then you're.
So I'm running 50% utilization in both places. Okay. Yeah.
But x of I equals x of 0.
If x of I, well, if x of I equals x of 0, you're either going to be all true or all false, right? So I'm going to run 100% utilization because everybody's either going to go true or false, and the other block gets skipped.
You could make it if I is 0 mod 8.
I is mod 0 mod 8, or let's say I change my input data such that every 8th item is going to trigger a true, and all other ones. Okay, so that'll get me 1 orange bar and 7 blue bars. I'm still not guaranteed. If those are equal cost things, I'm running 50% utilization. Half the time on 7 8, now the other half the time on 1 8.
I thought it was just an if statement and no else, so we're only running the if. That's what we were discussing.
Oh, I see. If you're only running the if. Okay, yeah, if you're only running the if. I was thinking about if it's an if else. Okay. Yeah. But you're almost there. We've almost got it. So if you send 1/8 of the iterations down the if, 7/8 down the else, I'm still at 50% utilization unless we make some assumptions about the cost. If I send 1 iteration down if, and if is a billion instructions, and 7/8 down else, and that's a cheap path, which is almost the same basically as what you're doing. Yeah, exactly. So you see that? So I can make this chip with an if else run at 1/8 performance. And by essentially making the if clause very cheap, the else clause very expensive, and making sure when I'm running the if clause, only 1 out of 8 are actually running. But yeah, so that is conceptually equivalent to your suggestion. Okay. This can be a problem, right? And on modern Intel hardware.
So I think I got it there by making it dependent on I, mod n, like I said originally. But it required like another if inside of here, which he said it only using a single if statement.
Is 8. So on modern GPU hardware, that vector width could be as high as sometimes 32. So you might be like, well, if I mess things up, if I'm running at 132 of my total peak performance, that's a little frustrating sometimes. Some vector width is 8. So on modern GPU hardware, that vector width could be as high as sometimes 32. So you might be like, well, if I mess things up, if I'm running at 132 of my total peak performance, that's a little frustrating sometimes. Just some terminology.
The vector width, let's see. On AVX 512, what is the vector width for 32-bit integer values? So yeah, I mean, we're at 16 and he just said 32.
Well, if I mess things up, if I'm running at 132 of my total peak performance, that's a little frustrating sometimes.
That's pretty interesting. That is pretty interesting that it's like half the width of a GPU.
Terminology, you'll hear.
And that's for 32-bit values. If you go down to lower integer sizes, you can get obviously higher width.
Like sometimes 32. So you might be like, well, if I mess things up, if I'm running at 132 of my total peak performance, that's a little frustrating sometimes. Just some terminology. You'll hear, especially if you read a lot of GPU programming stuff, you'll hear people go, you have to have coherent execution, you have to have coherent execution. Coherent execution is just a kind of a jargon and slang for saying
Instruction stream coherence or coherent execution, property of a program where the same instruction sequence applies to many data elements. Coherent execution is necessary for SIMD processing resources to be used efficiently. Coherent execution is not necessary for efficient parallelization across different cores, since each core has the capability to fetch decode a different instruction from the thread's instruction stream. Divergent execution, lack of instruction stream coherence in a program.
my loop, everything's kind of a jargon and slang for saying I have a program where all of the iterations of my loop, everything's going on, needs the same instruction stream. And the lack of coherence is often called divergence, meaning like you think about it as like different control paths are needed. So divergent code will not run well on a SIMD architecture like this. Coherent code will run at high utilization. And here, this slide's just some extra facts that you can see on your own, where the widths vary from about 4.
AVX2 instruction, 256-bit operations. You can get 8 32 bits or 4 64 bits. And 8 wide floats. So the floats would be what? 8 wide float would be 32-bit float. And then we have AVX 512, which is what I'm running on this machine. So we get 16 times 32 bits, basically double. And then ARM Neon instructions are 128-bit operations. They're half of AVX2. Instructions are generated by the compiler. Parallelism, explicit requests by programmers using intrinsics. Parallelism conveyed using parallel language semantics. E.g. for all example. Parallelism inferred by dependency analysis of loops by auto-vectorizing compiler. That's the only one that I've experienced so far. I haven't written my own intrinsic code, but I have written code that the compiler auto-vectorizes. Explicit SIMD. SIMD parallelization performed at compile time. Can inspect program, binary, and CSIMD instructions. There's an implicit SIMD that the CPU does? I don't know about that.
Especially a lot of the ARM SIMD instructions, all the way out to about 32 wide SIMD on a modern high-end GPU. Okay. I will create a supplemental video talking a little bit about some slight differences. I will create a supplemental, especially a lot of the ARM SIMD instructions, all the way out to about where the widths vary from about 4 wide SIMD on mobile chips, especially a lot of the ARM SIMD instructions, all the way out to about 32 wide SIMD on a modern high-end GPU. Okay. I will create a supplemental video talking a little bit about some slight differences between how GPUs implement this concept and how CPUs implement this concept. So I'll talk about it. I'll do it offline, kind of just watch the video to get into that. Okay. So it's kind of interesting. We have 3 different ideas that we're mixing and matching together. They are orthogonal ideas. We have the idea of superscalar execution, which is a hardware implementation.
See Kayvon's supplemental going farther video. Oh, interesting. It's probably not available to me then, because I didn't see it on YouTube, and he said the videos for this past year is not available. Kayvon SIMD going farther. So K-A-Y. Going. That's exactly the. This is on fall 23 though. Interesting. So it should be here. This is lecture multi-core. I think I can do this, right? Multi-core SIMD. Is that this one? Going. Yeah. Okay. It should be available. I don't see it. Going farther. This says Kayvon supplemental going farther video, but there should be something like going farther. Kayvon SIMD going farther video. Well, what is his name again? Maybe if I search for his actual name, this dude here. Delete the SIMD, maybe? Okay, well, I can't find it. I'll come back to this if he mentions it. So implicit SIMD, so this is compiler generates a binary with scalar instructions, but n instances of the program are always run together on the processor. Different cores. Hardware, not compiler, is responsible for simultaneously executing the same instructions from multiple program instances on different data on SIMD ALUs. I didn't even know that was a thing. SIMD width of modern GPUs range from 8 to 32. Divergent execution can be a big issue. Poorly written code might execute at 1/32, the peak capability of the machine.
All ideas. We have the idea of superscalar execution, which is a hardware implementation detail that requires no change to the program at all.
I really want to see that going farther video.
To get into that. Okay, so it's kind of interesting. We have three different ideas that we're mixing and matching together. They are orthogonal ideas. We have the idea of superscalar execution, which is a hardware implementation detail that requires no change to the program at all, which is if there are independent instructions in one instruction stream, the hardware figures it out and can execute two of them in parallel, inside the same core, inside the same instruction stream. We talked about SIMD, which is the program itself most of the time says, here are 8 operations or 32 operations that can be done in parallel. I have one instruction stream usually, and it's just issuing these vector or larger operations. Again, with an asterisk on, I will clarify that statement's not precise for GPUs, but conceptually it's the same. And then you have the idea of multi-core, which is taking one of these cores that can run one instruction stream, maybe with vector instructions, maybe with superscalar, and copying that as many times as you have the resources to fit on a chip. So here's some examples, right? This processor, 1 core, superscalar. This processor down here, 2 cores, no vector, no superscalar. This processor here, 4 cores, 8 wide vector, no superscalar. And I can keep mixing things together. Like if I had to draw a diagram of the myth machines, not quite that. Scalar, 8 vector. 4 cores, every core can run 3 instructions per clock. Those instructions might all be vector instructions. NVIDIA GPU, about 80 of these cores. Each one of those cores has about 128 ALUs that are actually organized in 32 wide SIMD instructions. All the same ideas, just different scales. Some of these scales cause Keynote to crash because you can't draw the diagram. Good. Per core. Superscalar execution is the core is given one thread. That thread has a sequence of instructions. If it finds ones, because those instructions are in one thread, they're all reading and writing the same registers. There's only one thread, one execution context. If there happens to be the ability to find a couple of those instructions that can be run in parallel, this chip may find up to 3.
How many vectors is one core run in this?
4 cores. So often I want you to think about what's going on in a core, because like multi-core is just replicating things. Inside a core, I have one instruction stream. Registers right here. This core is running instructions in the instruction stream. Every ticket runs the next one. If it happens to find instructions that are independent, maybe it can run 3. If those instructions are 8 wide vector instructions, you'll get 8 wide vectors. So if you count here, there's 24 execution units. Peak performance of this core is 24 operations per clock. Peak performance of this chip is 4 times 24, 96 operations per clock. Okay? Peak performance of this chip is 128 times 80, and I can't do the math, operations per clock. Okay? Yes?
8 wide vector operations.
An 8 wide, like I want I want you to think about an 8 wide vector instruction. It's an instruction, just like another add instruction. And an add instruction usually is add this scalar register to the scalar register, which means like add 42 and 10, and you get 52. A SIMD vector instruction is an instruction that says, please add this 8 wide vector to this 8 wide vector, element-wise. So a single instruction does 8 scalar operations. Like you're writing code in NumPy or PyTorch, and you have an 8 wide tensor and another 8 wide tensor, and use the plus operation. That's a machine instruction. Okay? Yep.
When will this change, like when this change happen, that like when we move from this like vector style to
On x86, it was something called SSE instructions. I don't know. They're 4 wide. I feel like they're probably early 2000s. Yeah. And they were 4 wide for RGBA for simple graphics operations. Yep. Okay. Kind of beat early in the lecture about the effects of latency, right? And we motivated caches as being this thing in a processor that is critical to not running at 250 at the peak performance waiting on these things. And I also told you a little bit about, well, one of the major hogs of resources in a modern chip is putting these big caches everywhere you can in order to avoid stalls due to memory. Right? And we talked a little bit about this access pattern. About the effects of latency, right? And we motivated caches as being this thing in a processor that is critical to not running at 250 at the peak performance waiting on these things. And I also told you a little bit about, well, one of the major hogs of resources in a modern chip is putting these big caches everywhere you can in order to avoid stalls due to memory, right? And we talked a little bit about this access pattern where even though it was like really predictable and going right through the array, when we came back around, we still missed. We still missed, even though. So another thing that processors have in them, in addition to caches, is they actually have prefetchers. They actually analyze your program in the same way that they're looking for independent instructions in superscalar. They might look at your access pattern and go, I'm pretty sure you're going to be accessing this variable next, so I'm going to go ahead and preload that address for you. And so in a predictable access pattern like I just showed, it's very possible that this may not, I got to fix that, it's not conflictness. It's very possible that that last load might have been predicted and actually might be there. But not all code runs like this, right? Like sometimes it's hard to predict something. Like imagine you're walking through a linked list, or imagine you are you have some value and like you just compute a value and you're going to do an array lookup based on that value. A very common thing is like give an array of indices, go look up the data at that index or something like that. So you can't, in these throughput computing days, you can't really assume that you can predict what's coming. And in order to make room for all of these cores, we might have taken out of the prefetching logic. We might have shrunk the size of the cache. So we made it even more likely that we're going to take cache misses. Yet we packed the machine full of ALUs, which means we're going to make even more memory accesses. We need to make them even faster to keep all these things busy. So we've really created ourselves a little bit of a problem here. We have these amazing processors that have all this stuff, yet they're waiting on memory. And so in my house tonight, I had a PhD student graduate a couple weeks ago, and we're inviting him and his girlfriend over for hot pot. And so there's going to be like a lot of prep going on. And so I want you to think about some real life examples. Let's say you're cooking in the kitchen. Let's say you're doing your laundry tonight, because it's already day 4, so you might be onto that. How many of you, when you're doing your laundry, put the load in the washer and sit there and wait? How many people start boiling water and sit there and wait until it's ready before you put the food in? What do you do instead? I mean, maybe some of you do. Wait, I don't know. If not, you're going to come away from this class with a good life hack. So what do? You put your laundry in, you boil your water. What's going on? You sit around and wait? I mean, you watch all of my lectures on 2x, so I know you don't sit around and wait while you're. So what do you do? Sorry? You do something else, right? And you do your homework in 149. So the main idea is if you know something that you need to be done is not going to be done for a while, you just go do something else. Now that means you have to have something else to do. Like maybe all of your lives are such that, given anything else I have to do, I'd rather sit here and wait. But most of us have multiple things that we can do that we'd rather do. So this gets to the last idea today. We're going to build processors that, remember, like I just gave you a chip that, what did I say, had 16 cores times 8 wide SIMD, so it had 128 execution units in it, which means it can do 128 things at once. But imagine you're doing some machine learning operation. Imagine you're processing a 4 megapixel photo off your iPhone, or I guess it's 8 or 12 these days. You have millions of pixels. You have way more things that you need to do than the things you can actually do at once. And so if you're going to sit there and wait on some of those things, let's just go start working on something else. Okay, so here's the main idea. We're going to take that core that we had. Notice that in this diagram, it's a single instruction stream. Got no superscalar, 1 instruction per clock, but I'm going to allow that to be a vector instruction just for the sake of things. Okay, and now what I'm going to do is I'm going to take the execution context, the registers, and the address space associated with them, and now I'm going to duplicate this. Okay, so remember I said that an instruction stream, the execution context represents the state of the instruction stream, or in other words, we could say the state of a thread. Now what I'm going to do is the processor, the orange and the yellow is staying exactly the same, but I'm going to give that processor the ability to hold state for 4 instruction streams, for 4 threads. Okay? So we're going to start executing normally. So now we're going to say, look, for this processor, your program is going to say create 4 threads now. For one core, 4 execution contexts, here, have 4 threads to do. And so the processor is going to move along, and it's going to run a thread. That's what I'm kind of trying to show you here. It's going to run this thread. Maybe it's executing some of the instructions, and at some point it gets to a load. Cache miss. This thread cannot make progress for a long time. Let's say this is the point at which it becomes runnable again because the data came back from memory. That was the 250 cycles that we were waiting. Cool. So do you think this core is going to stay idle? Nope. The minute it's like, I can't make any progress, it's like, I gotta wait. I'm like, I got 3 other threads that I can go make progress on. So we're going to swap. And when I say swap, I'm talking about the hardware just starts executing instructions from the next thread. Like no delay or anything. It's just, oh, I can't make any progress with this instruction stream. I've got another one sitting here. Next cycle, I'm going to run that one. I'm going to run whatever's available. And then maybe that one stalls, but we got another one. Maybe that one stalls. We got another one. By the time that 4th one has stalled, we are past the point in time when this one is ready. So we can get going again. We can just start working on that other thread. And let's say it finishes, and we move on and so on. What is the utilization of this processor? 100%. What is the latency of actually finishing any one thread? It's actually longer because it actually had this time where it could have started running here, but it actually runs here. Okay? That's the last big idea here. Is we're actually slowing down the amount of the wall clock time to get anything done in order to get everything done quicker because we're running at 100%. I'll stop there. Okay, so we'll review this again next time. We'll start, and then we'll get into
So we are on slide 74. And if we go back here, yeah, part 1, it's like we gave up here. But there's a whole heck of a lot more to this lecture.
the superscalar. But you have everything you need to get started and do 90% of your homework assignment.
Okay, well. I'm going to take a break here for dinner, and then I'll get back on after dinner and some cardio, and I will start on the first assignment, because he said just at the end of the lecture there that that's all you need. And I think I've done some of this assignment already previously. So CS 149. Sorry. So readme, I'm gonna say did that and did that. Okay, the assignment is here. So let's go ahead and just open that. Oops. Is it Alt? Cat out, grep, GitHub. It's gonna be this guy here. So we'll clone this thing down as a submodule. Let's say git submodule, add this thing as, yeah. Boom, 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 boom. Git CI, we'll just say add submodule for first assignment. CD into AS here. And then we got all of our good stuff here. Cool. Alright, we'll pick up on this assignment after I'm done with my cardio and my dinner. Cool. I'll be back on later tonight. Later.